Hello, fellow sapiens, and welcome to Sleepless Homo, a quiet corner of the internet where curiosity doesn't need caffeine and science is spoken slowly enough for the tired brain to keep up. Wherever you are, whether you're preparing to sleep, stretching your legs on a long drive, stirring something on the stove, or working quietly with headphones on, this space is here to help your mind uncoil, one slow story at a time. If you find yourself appreciating this kind of deep, carefully told science, the kind that doesn't shout, doesn't speculate wildly, and doesn't pretend to have all the answers, I'd invite you to gently like the video and subscribe. It helps support long-form storytelling that prioritizes evidence over drama. This is a channel for the quietly curious, for those who feel the pull of deep time but still want to get up for work in the morning. And if you're the kind of sapiens who ends up drifting off in the middle of one of these chapters, no worries. I've added timestamps in the description so you can pick the story back up the next day, right where you left it. Because this journey, from the end of the dinosaurs to the first apes who looked a bit like us, is worth hearing from start to finish. And as always, stay curious, stay calm. Now, let's talk about what really happened after the dinosaurs disappeared, and how Earth began writing a whole new chapter without them. It is sometime around 66 million years ago. The sky above what is now the Gulf of Mexico is silent, warm, and seemingly ordinary. Beneath it stretches a shallow tropical sea. There are no cities, no continents as we know them, and certainly no witnesses. But the planet is about to experience one of the most violent hours in the history of life. A single object is hurtling toward Earth from the dark silence of space, and it is moving at speeds faster than anything the human mind evolved to comprehend. We now believe it was about 10 to 12 kilometers wide, roughly the size of Mount Everest, or perhaps a little smaller. But its speed is everything. This is not a slow descent. It is racing through the upper atmosphere at around 65,000 kilometers per hour. Or put another way, it is falling from the sky at almost 20 times the speed of a bullet. We call it the 𝐓�ဣ𝐿𝐼 impactor, named after the quiet Yucatan village that now sits near its buried crater. But it did not come with a name. It came with heat, it came with pressure, and it came with physics that don't negotiate. When the asteroid struck the Earth's surface, it did not land so much as explode on contact. The energy released in that single moment has been estimated to equal more than 1 billion Hiroshima-scale atomic bombs. Not 1,000. 1 billion. The heat of the impact flash was enough to ignite forests thousands of kilometers away. The pressure wave moved faster than the speed of sound, flattening everything in its path. This was not just a loud event. It was a silence generator. Animals caught in its radius did not have time to run, or process, or scream. They simply vanished. And this was only the beginning. The impactor hit a geological formation rich in limestone and sulfur-bearing rock. That detail might seem boring, but it is everything, because when that much sulfur is vaporized, it turns into aerosols that climb into the upper atmosphere and stay there. These aerosols reflect sunlight away from the Earth, blocking the warmth that living systems depend on. They don't just cause darkness, they cause cold. Global photosynthesis began to fail almost immediately. The temperature began to plummet. Food chains cracked from the top down and the bottom up. The world's dominant species, the dinosaurs, were not wiped out in a single afternoon, but their dominance ended in one. Before that chain of events even began, the physical effects of the impact were still unfolding. At ground zero, the rock of the Earth's crust liquefied under the force of the collision. Molten material was blasted into space and fell back to Earth across the entire planet. Tiny glass spherules called tektites rained down over what is now North America, Europe, and parts of Asia. These particles heated up the atmosphere as they re-entered, creating a global infrared pulse. The air itself became an oven. For a few minutes, the surface of the Earth was hotter than an industrial furnace. This may have ignited wildfires on every continent. Not in one place, everywhere. Ash clouds spread, the sky darkened, oxygen levels fell, the planet began to turn into a graveyard. But not evenly. The destruction was shaped by geography, topography, and luck. The impact also triggered earthquakes that may have reached a magnitude of 11 or higher on the modern scale. For comparison, the strongest earthquake in recorded human history, the 1960 Valdivia quake in Chile, was a 9.5. Chicxulub's tremors would have been felt across the globe. Entire coastlines shifted. Landslides crushed ecosystems. In the oceans, a mega tsunami formed, possibly hundreds of meters high. Some models suggest it circled the globe multiple times. In regions like what is now the western interior seaway of North America, sediments record sudden mass burials of marine life, jumbled in chaotic layers, the frozen signature of something unspeakable. Scientists studying the crater today have mapped its shape using seismic tomography. It is buried beneath hundreds of meters of sediment, but it is still there, 180 kilometers across and at least 20 kilometers deep. It is the best preserved large impact crater on Earth, and perhaps the most consequential. In its layers we find shocked quartz, melt rock, and a global iridium anomaly. Iridium is rare in Earth's crust, but common in asteroids. And around the world, in sites from Montana to Tunisia, we find a thin clay layer marking the boundary between two geological ages, the Cretaceous and the Paleogene. This line contains elevated levels of iridium, soot, and microtectites. It is not just evidence of impact, it is evidence of global trauma. For decades, this event was just a theory. It wasn't until the late 1970s that Luis and Walter Alvarez published their paper proposing that a sudden influx of extraterrestrial iridium might be the signature of a cosmic collision. The idea was ridiculed at first, but as the evidence piled up, the crater, the spherules, the global soot, the consensus shifted. It is now widely accepted that the Chicxulub impact played a central role in the fifth mass extinction. Though, as always, science leaves room for nuance. Volcanism in the Deccan Traps of India may have contributed to the environmental stress, so might have long-term climate shifts already in motion. But the impact was, as far as we can tell, the final blow. The exclamation point on the Mesozoic era. What is remarkable is how fast it all unfolded. Within minutes, vast regions were in flames. Within hours, the food web had begun to crack. And within days, the Earth's climate began its descent into darkness. What followed is another story. But in this moment, in this catastrophic first act, we are left with a single haunting idea, that the most powerful event in the history of complex life on Earth may have lasted less than one human afternoon, from sky to silence. There is no moral to this, no prophecy, only physics. The dinosaurs were not dumb, slow, or obsolete. They were the most successful large animals in Earth's history, thriving across every continent for more than 160 million years. And yet, none of that mattered when the rock fell. That is the nature of extinction. It does not negotiate with success. It does not check your resume. It only measures momentum and impact. The world did not end that day, but one world did. The world of the ammonites, the pterosaurs, the great marine reptiles, the land giants, the intricate ancient food webs of the Cretaceous seas and forests. That tapestry was shredded in hours, and the Earth would spend millions of years recovering its complexity. We often like to imagine apocalypses as slow, but some are sudden. Some strike from the sky with no warning and no mercy, and the planet moves on without a sound. Today we remember that day not because we were there, but because we eventually became the kind of animal that could dig up its memory. One layer of clay, one crater, one fossilized fern at a time. So the question that hangs in the air is simple. If life can be ended that quickly, how does it begin again? That's what we'll explore next. Can life survive in a world without sunlight? That is the question that quietly followed the explosion. Because while the moment of impact made the most noise, it is what happened after that nearly finished the job. In the days and weeks that followed that singular collision, Earth began to shut down, not explosively, not even visibly at first, but chemically, globally. From the top of the atmosphere to the base of the oceans, the planet began to unravel, not with a bang, but with a dimming. What we now call the KPG boundary marks not only the end of an era, but the beginning of something far stranger, a winter without snow, a season without end, and an ocean slowly suffocating beneath the weight of a sky it could no longer see through. For tens of millions of years, Earth had been a vibrant system powered by solar energy. But after the asteroid strike, that power source was choked. The skies filled with ash and chemicals. Photosynthesis, arguably the single most important biochemical process on this planet, faltered. And in the vast, unseen spaces beneath the waves, something almost unfathomable began to take place. Silence. The primary driver of this darkness was not just the dust from pulverized rock. It was the sulfur. The asteroid's point of impact struck a carbonate-rich marine shelf loaded with gypsum and anhydrite. When these compounds were vaporized, they produced massive amounts of sulfur dioxide. This gas didn't just sit at the surface. It climbed high into the stratosphere, where it combined with water vapor to form fine sulfuric acid aerosols. These tiny droplets reflected incoming sunlight back into space, scattering the blue and dimming the warmth. And because they floated above the weather systems, they stayed there. Not for days, but for months, possibly for years. The effect was a kind of planetary shroud, a veil so thin you could not hold it in your hand, but thick enough to turn off the sun. At the equator, day became a kind of twilight. At the poles, already seasonally dark, that twilight never lifted. And beneath this murky atmosphere, Earth's climate began to spiral. Not in a straight line, but in feedback loops. Without sunlight, surface temperatures dropped. Evaporation slowed. Rainfall patterns collapsed. And worst of all, the base of the food chain began to starve. Most of the living biomass on this planet depends on light. Not directly, but one step removed. Tiny organisms called phytoplankton sit at the root of the oceanic web. They use sunlight to produce sugars, forming the primary source of energy for zooplankton, small fish, and eventually everything else. But they cannot function in the dark. Sediment cores from ancient ocean basins confirm this collapse. In layers dated precisely to the years following the boundary event, we see a dramatic drop in organic carbon. Microfossils that once teemed with foraminifera, those tiny shelled protists that drift in every sea, suddenly disappear or give way to simpler, hardier forms. There is a spike in what's known as the disaster taxa, species that thrive in disturbed, nutrient-poor conditions. These are the cockroaches of the microbial world. Survivors, yes, but only just. This disruption was not uniform across the oceans. In coastal upwelling zones, where deep waters bring nutrients to the surface, recovery may have started sooner. But in the vast central gyres of the open ocean, it likely took thousands of years for primary productivity to return to pre-impact levels. The full scale of this shutdown is hard to overstate. It was not just a matter of fewer fish. It was a collapse in the very logic of life. The biological pump that drives carbon through the ocean stalled. Oxygen levels in deeper waters declined. Marine snow, the constant drift of organic matter from surface to seafloor, slowed to a trickle, and entire ecosystems built on that nutrient flow began to starve in the cold and dark. At the same time, on the continents, a different kind of silence was forming. The plants that had survived the immediate blast now faced a new enemy: darkness. Without photosynthesis, even the most resilient flora began to weaken. Forests, already scorched, stopped growing. Pollen records drop off. Spores from fungi, on the other hand, spike dramatically. This is the so-called fungal spike, found in boundary sediments around the world, from North America to New Zealand. It is not evidence of a happy bloom. It is evidence of decay, of death feeding death. Fungi thrive on biomass, and in the months after the sky dimmed, there was plenty to decompose. But not everything was passive. In the atmosphere itself, chemical reactions continued, reshaping the composition of the air. The sulfuric aerosols that blocked the sunlight also acidified the upper atmosphere. As they slowly rained out, they brought with them a toxic drizzle of sulfuric acid. This was not the kind of acid rain associated with industrial pollution in the modern era. This was global, persistent, and potent enough to alter the chemistry of lakes, rivers, and even soils. Freshwater ecosystems, already fragile, were particularly vulnerable. Amphibians, with their sensitive skin and complex life cycles, likely suffered immensely. But again, the fossil record here is fragmentary. Most of what we know is indirect. Patterns in sediment, shifts in isotope ratios, and the sudden absence of life where once there was continuity. In the ocean, Calcium carbonate-producing organisms were among the hardest hit. Coral reefs vanished. Coccolithophores, which form chalky plates from calcium carbonate, declined severely. Ocean acidification, driven by both atmospheric CO2 and sulfuric deposition, altered the buffering capacity of seawater. This may have interfered with shell formation, disrupted metabolic processes, and created a hostile environment for any species not adapted to chemical instability. Some of this damage may have been temporary, but temporary, in geological terms, still means thousands to hundreds of thousands of years. It is worth noting that not all models agree on the exact timing and duration of these effects. Some suggest that the worst of the cooling and darkness may have lasted only a few months. Others argue for a longer, multi-year disruption, followed by decades of recovery. The truth is, we don't fully know. Earth does not keep a daily diary. What we do know comes from proxies, layered sediments, isotopic fingerprints, and rare fossils preserved in strange places. Science, in this case, is not an omniscient narrator. It is a detective, trying to reconstruct a murder scene where most of the evidence has already dissolved. And in that reconstruction, one fact keeps surfacing. The collapse was not just physical, it was ecological. In the wake of the impact, many of the organisms that had dominated the late Cretaceous simply lost their place in the system, not because they were inherently less fit, but because the system itself changed too fast for them to adapt. Evolution is a powerful tool, but it moves on geological time. Extinction can happen in a single generation. To understand the severity of this shift, consider that nearly 3/4 of all species on Earth disappeared. Not just dinosaurs, not just big things, but entire lineages, ammonites, pterosaurs, most marine reptiles, whole categories of plankton. What survived did so not because of superiority, but because of circumstance. It turns out that being small, cold-tolerant, generalist, or lucky was better than being dominant. And all of this started not with the impact, but with the sky. When the clouds thickened, when the photos stopped flowing, when the chemical composition of the atmosphere changed, life followed. Not immediately, but inevitably. The Earth did not become a snowball, but it became a dim, cold, chemically unstable world for long enough to rewrite the biosphere. The haunting part is this: the actual rock only hit for a moment. The physics of collision lasted seconds, but the consequences rippled through the system for thousands of years. That is the strange, slow cruelty of planetary feedback loops. A single high-energy event can tip the balance, and then the balance keeps tipping. What happened next would depend entirely on who survived this long twilight. But in this particular act, the focus is not on survival. It is on silence. The silence of photosynthesis failing, of oceans turning still, of ecosystems pausing as if held underwater. And the question that follows is no longer how the dinosaurs died. It is how anything lived. That's what will follow next, but only after the darkness lifts. Why did the tiny, the hidden, and the weird make it through? It is one of the most important questions in all of evolutionary history, because survival is not a given, especially not in the year after Earth lost its sky. By around 65 million years ago, the worst of the impact winter had begun to wane. The thickest aerosols had slowly rained out of the atmosphere, the sulfur clouds had started to dissipate, and a fractured sunlight was beginning to return. But this was not a return to normal. It was the aftermath. The planet was still colder, quieter, and biologically simpler than it had been for millions of years. The great dynasties of the Cretaceous were gone. Their fossils were still soft in the mud, but around them, life was stirring, not roaring back, whispering. Across the globe, scattered in soils, under rocks, and beneath the forest litter, small organisms were still alive. Not just microbes or fungi, but vertebrates, animals with backbones, blood, and lungs, creatures that somehow had made it through the chaos. The fossil record does not preserve their thoughts or their fears, but it does preserve their patterns. And those patterns tell a subtle story, one that hints at what allowed some to survive when nearly everything else perished. What we begin to see in this window of time is not just extinction, it is resilience. And that resilience does not belong to the mighty. It belongs to the overlooked. In modern ecosystems, we are often drawn to the charismatic species, the tigers, the whales, the ancient giants with teeth or armor. But evolutionary success does not always come with a fanfare. Sometimes it hides underground. In the years after the end Cretaceous extinction, the creatures that fared best were often the ones no one noticed. Many of them lived in burrows or crevices, or along the muddy edges of what remained of rivers and coastlines. These habitats had something in common. They buffered change, temperature shifts, acid rain, falling debris. None of these forces penetrated the soil very deeply. In caves, humidity could remain stable. In burrows, the air was cooler. In the quiet places of the earth, catastrophe moved a little slower. The survivors were not just hiding. They were metabolically different. Many had low energy requirements. Some could enter torpor or hibernation. Others were cold tolerant by default. It is possible that during the darkest periods, these animals simply waited. Not intelligently, not with planning, but with biology. A slowing heartbeat, a shivering metabolism, a body geared for pauses. Hibernation is not a magical trait, but it is a profoundly useful one when the food chain disappears. And evidence suggests that even some early mammals at the time had already evolved these capabilities. Not all of them, but enough. There is a tendency in our storytelling to make extinction feel like a single event, a line. But in reality, it is a gradient. Some species may have vanished in a single day. Others faded over years or decades. And in that fading, there was space for the small to persist. Amphibians, for instance, left behind clues that some lineages weathered the storm. Frogs and salamanders, which spend much of their life in moist microhabitats or underground, appear to have passed through the boundary without a dramatic drop in diversity. Similarly, turtles, slow, unassuming, and often aquatic, continued into the Paleogene with surprising stability. These were not apex predators or ecological engineers. They were survivors by design. Low metabolic rates, opportunistic diets, and in many cases, protective shells. Among the vertebrates, a few groups show what paleontologists call a Lazarus effect, a disappearance from the fossil record followed by a sudden reappearance. This does not necessarily mean they went extinct and re-evolved. It often reflects a collapse in fossilization conditions, followed by a rebound. But it still tells us something about how patchy survival was. In some regions, entire groups may have vanished. In others, they held on in small, isolated pockets. These pockets became refugia, places where the threads of life could be preserved long enough to be rewoven. Marine environments had their own version of this phenomenon. In shallow coastal zones where temperatures and light levels were more variable, some benthic organisms persisted. Detritivores, those unglamorous feeders of debris, found enough decaying matter to get by. Scavengers, filter feeders, and generalists filled the vacuum. In deep-sea vents, life was even more insulated. These ecosystems, powered by chemosynthesis rather than sunlight, may have felt the impact less directly. Their energy came not from the sky, but from Earth's internal heat. And while they did not dominate the recovery, they remind us that life's foundations can be surprisingly diverse. It's important to say that we do not know exactly which individual species survived the immediate aftermath. Fossils do not come with timestamps accurate to the month or even the century, but we can track clades, lineages that branch into new forms over time. And what we see is that the survivors often shared a few characteristics. They were small, they had flexible diets, they could tolerate stress, and they did not rely on large interconnected ecosystems to survive. That last point is crucial. In a shattered biosphere, food webs become patchy, keystone species are gone, symbiotic relationships dissolve, and only those who can adapt alone, or nearly alone, persist. Some birds also made it through, though not all. The fossil record suggests that many archaic avian groups perished, while the ancestors of modern birds, those closer to what we now call neornithes, somehow endured. The exact reasons are still debated. One hypothesis is that ground-dwelling birds had a survival advantage. Another suggests that seed-eating species could find food in a world where insects and fruit were scarce. Whatever the case, the birds that emerged in the early Paleogene were not glamorous. They were scrappy, functional, adapted to a changed world. We must also be careful not to read too much design into this. Evolution is not forward-thinking. It does not optimize for future disasters. It only filters based on what works right now. The The species that survived were not better. They were different. They fit, accidentally, into the narrow cracks left behind. And those cracks, cold burrows, dark soils, isolated estuaries, became the cradle for the next act of life. There is an eerie humility in this. The world's most powerful organisms were erased in the blink of a geological eye. But those that squeaked, burrowed, scavenged, and waited, those moved forward. Not because they deserved to, but because they could. And the systems they seeded were strange. Low-diversity ecosystems dominated by generalists, forests full of fungi and ferns, oceans ruled by microbial mats. It would take tens of thousands of years for complexity to return. But it did, slowly, on the backs of the quiet ones. Today, many of the creatures that now dominate the Earth can trace their ancestry back to these survivors. Not directly, not cleanly, but ancestrally. The lineages that persisted through the KPG bottleneck went on to radiate into mammals, birds, reptiles, and fish that would redefine the biosphere. But none of that was obvious in year one. At that point, the world was just trying to hold on, to avoid slipping further. We tend to think of the big picture when we tell stories of extinction and evolution, but survival is often local. It is the animal that finds shelter under the right stone, the egg that happens to lie just far enough underground, the fish that stays one layer below the acidified surface. These are not myths, they are physics, chemistry, biology in crisis mode. And so the question we are left with is not just who survived, but what they tell us about survival itself. That maybe resilience does not always look like strength. Maybe it looks like stillness, like hibernation, like eating detritus when the forest is gone, or burrowing deeper when the air turns poisonous. In the year 65 million, before present, life on Earth looked nothing like it had the year before. But it was still here, shivering perhaps. But here, the Great Extinction was not absolute. It was selective. And what it selected were the ones small enough, quiet enough, and strange enough to slip through the cracks. So the next time we ask what kind of traits help life endure catastrophe, the answer may not be claws or size or dominance. It may be adaptability, modesty, or just being in the right hole at the right time, because sometimes that is enough. And from there, evolution can begin again. What happens when the rebound from a firestorm ends in ice? In the years that followed Earth's most violent hour, the sky slowly cleared, the sulfuric haze thinned, and a pale, broken sunlight began to reach the surface again. It might have felt like relief, but nature does not recover in straight lines. The rebound from mass extinction is rarely smooth, and in this case, the path out of darkness led not toward warmth, but toward a chill that would grip the planet for thousands of years. It was a cooling not born from calm, but from chemistry, physics, and the long aftershocks of planetary trauma. The immediate crisis had passed, but the Earth, still reeling, veered too far in the opposite direction. The firestorm had faded. The deep freeze was beginning. From around 64 to 60 million years ago, the Earth entered a period of sustained climatic instability, not a full-blown ice age in the modern sense. There were no massive continental glaciers, but the poles, once lush and temperate, began to cool in ways that disrupted the balance of the planet. Sea surface temperatures dropped, atmospheric circulation patterns shifted, and deep ocean currents, which depend on temperature gradients and salinity, began to behave in new and unpredictable ways. The planet was not simply recovering, it was overcorrecting. We know this not from guesswork, but from sediments. Deep-sea cores drilled from ancient ocean basins hold chemical signatures of past climates in the form of oxygen isotopes. The ratio between the heavier isotope oxygen-18 and the lighter oxygen-16 can tell us about the temperature of seawater when the shells of tiny marine organisms, like foraminifera, formed. In these cores we see a distinct isotopic signal during this interval, suggesting that global temperatures were lower than expected for a post-extinction greenhouse world. Something had interrupted the warmth. One contributing factor may have been the lingering carbon debt. The impact event had sent massive amounts of dust and aerosols into the sky, but it had also disrupted the carbon cycle in less obvious ways. With primary production shut down in both oceans and on land, Vast quantities of carbon were no longer being absorbed through photosynthesis. At the same time, wildfires had released carbon dioxide, but not at the levels associated with volcanic events. The net result may have been a temporary drawdown of atmospheric greenhouse gases. Combined with reduced solar input, this could have tipped the system into cooling. Earth's thermostat is sensitive, and when both the sunlight and the carbon budget drop at once, the feedbacks can cascade. But what makes this particular cooling episode so interesting is that it occurred in a world still geologically configured for heat. At the time, continents were positioned differently than they are today. The supercontinent of Gondwana had already fragmented, but the Atlantic Ocean was still narrow. India was racing north toward Asia. Australia had not yet broken free of Antarctica. There were no permanent polar ice caps, and yet the poles began to lose their warmth. Fossil evidence from regions like Antarctica and the Arctic suggests that lush forests began to decline. Pollen grains from broadleaf plants grow sparse in sediment cores. Cold-adapted conifers begin to appear more frequently. And in the oceans, deep-water species show signs of shifting distributions, some disappearing entirely, others migrating toward the equator in search of more stable conditions. This drop in global temperature also altered the oxygen dynamics of the ocean. Cold water holds more dissolved oxygen than warm water. As temperatures dropped, some deep-sea environments may have become more oxygenated, while surface waters, still recovering from productivity loss, remained stressed. These oxygen shifts would have affected not just the chemistry of the ocean, but the types of organisms that could survive there. Certain groups of plankton, for instance, are sensitive to oxygen availability, and fish, especially in their juvenile stages, require specific oxygen levels to thrive. In a world where surface productivity was already fragile, these chemical changes may have prolonged the ecological bottleneck. On land, temperature changes translated into altered rainfall patterns. Cooling affects the position and strength of the Hadley cells, those great atmospheric engines that drive tropical rainfall and trade winds. As these systems shifted, precipitation belts moved. Regions that had once been wet became dry. Forests struggled. Some areas may have experienced a kind of proto-savanna landscape, open woodlands rather than closed canopies. Not yet the grasslands that would dominate later, but a step in that direction. And in this transitional space, plant communities had to adapt to less predictable moisture, colder winters, and shorter growing seasons. But again, this was not a glaciated world. There is no evidence of massive continental ice sheets during this time. The cooling was moderate by modern standards. But what made it consequential was its timing. Life was still on its knees. Ecosystems were simplified, fragile, and fragmented. Any additional stress, such as a global chill, could stall recovery. Evolution requires stability to diversify. In a world that keeps changing, survival becomes the full-time job. In the fossil record, we see this slowdown in action. Speciation rates remain low for several million years after the boundary. Extinction rates stay elevated. Ecosystems are dominated by generalists. Specialists, which tend to evolve in stable environments, are rare. It is a world in holding pattern, not collapsing, but not yet thriving either. And climate instability is one of the reasons why. It is worth noting that not every region cooled in the same way. Local climates are shaped by geography. Proximity to oceans, mountains, and currents can create microclimates that differ dramatically from the global average. In some places, temperatures may have remained stable or even warmed slightly. But the overall signal, seen in isotopes, pollen, and ocean sediments, is one of decline. A long, shallow trough in Earth's thermal history. One open question is how much of this cooling was directly linked to the impact event, and how much was driven by other forces. Some researchers have pointed to the timing of volcanic activity in what is now India, the Deccan Traps. These eruptions began before the impact but continued afterward. They released not just carbon dioxide but sulfur gases and particulates. The exact role of these eruptions in post-impact climate is still debated. Some models suggest they may have prolonged the cooling. Others argue they helped warm the planet back up by releasing greenhouse gases after the initial aerosol effects faded. The truth is probably somewhere in between. Climate is not controlled by one dial. It is a system of interlocking gears, each moving at its own pace. So what does this mean for life on Earth between 64 and 60 million years ago? It means that recovery was not linear, that evolution did not sprint from the finish line of extinction. It limped, it hesitated, and it faced headwinds from a climate that had lost its bearings. Some species did begin to radiate. Ferns and fungi gave way to shrubs and flowering plants. Some fish and invertebrates found new niches. But the boom was yet to come. This was the pause before the pulse, the cold breath before the mammalian expansion. And it is in this pause that we learn something subtle about how life deals with instability. Because stability is not the default, it is the exception. Earth has always been a turbulent planet, and life has always had to adapt not just to violence but to confusion. This cooling episode reminds us that the aftermath of catastrophe is often its own kind of struggle, that the fire may have gone out, but the cold that follows can still kill. And so we arrive at a strange, quiet landscape, a planet no longer burning, but not yet blooming. The skies are clearer, the days longer, but the temperatures are uneven, the winds unpredictable, the oceans still trying to remember their own chemistry. It is a world waiting for something, for a spark, for a pattern, for warmth to return. That warmth would come, but not yet. And the haunting question that lingers is simple. How many times has life thought the worst was over, only to face one more trial just as it began to stand again? In this case, the chill was not final, but it left a mark, and what grew next had to grow through the cold. Who were Earth's first recolonizers after the apocalypse? When we imagine recovery after a mass extinction, we often look for the next big predator, the next dominant species, or the rise of some spectacular new creature. But before any of that can happen, something else must return first: plants. Without vegetation, there is no food web, no oxygen cycling, no soil stability, no framework for animals to live within. So when the skies began to clear, when the temperatures began to wobble towards something more livable, and when the fires stopped smoldering, the first true step toward rewilding the planet was not dramatic. It was green, or, at first, brown. From about 60 to 58 million years ago, large regions of the planet, especially across what is now North America and Eurasia, entered a quiet phase of biological reboot. The land was still scarred. Ash covered many surfaces. Soils were either stripped or chemically damaged. Microbial communities had been destabilized. In some places, tree roots were preserved as charcoal fossils, blackened remnants of forests that had burned at extinction's edge. But in the mud above them, signs of new growth appeared. Not towering trees or colorful blooms, but the simple and efficient pioneers of ecological recovery. The first clues come in the form of spores, specifically fungal spores. A now famous fungal spike appears in many sediment cores from this period, a sudden increase in the presence of fungal remains, right above the boundary clay that marks the extinction. This spike tells us something important. Dead biomass was everywhere. Forests had collapsed, and the remains of plants and animals alike were decomposing. And fungi, nature's great recyclers, had moved in. These were not glamorous organisms. They were mold-like, detritivorous, capable of breaking down lignin and cellulose and turning the apocalypse into mulch. Without them, recovery might have stalled before it began. As fungal activity increased, it primed the soil. Organic material, however damaged, was being converted into usable nutrients. And that allowed something else to follow: plants. Not the towering gymnosperms of the Cretaceous, not the complex, shade-tolerant species of mature forests, but pioneer plants, fast-growing, sun-loving, soil-stabilizing species that could handle disturbance. In modern ecology, we might compare them to fireweed or dandelions, species that don't wait for ideal conditions. They just show up and grow. Among these early recolonizers were members of the angiosperms, flowering plants that had already begun their evolutionary rise during the late Cretaceous. These were not ornamental flowers in the human sense, but functional innovations. Angiosperms produce seeds enclosed in fruit or other protective structures. This allows for more efficient dispersal and often quicker germination. In a devastated world, that is an evolutionary edge. Many early angiosperms appear to have been herbaceous rather than woody. They grew fast, reproduced quickly, and created ground cover that helped prevent erosion. They were, in essence, the biological scaffolding upon which ecosystems could rebuild. Fossil pollen records show a gradual shift during this time. In the immediate aftermath, gymnosperm pollen, especially from conifers, remains common in some regions. But as the years pass, angiosperm pollen becomes dominant in many cores, particularly in temperate latitudes. This suggests not just survival, but expansion. Flowering plants had weathered the extinction, and now they were capitalizing on the open niches. With less competition and more disturbed ground, they spread. And as they spread, they reshaped the land. One of the key challenges for plants in this period was not just regrowth, but re-establishing the symbiotic relationships that make modern ecosystems function. Many plants rely on mycorrhizal fungi, networks of subterranean filaments that help roots absorb nutrients. After a global catastrophe, these networks would have been disrupted. But as fungi recovered, these mutualisms could reform. Likewise, nitrogen-fixing bacteria, critical for building soil fertility, had to recolonize as well. These invisible alliances took time, but they were essential for the eventual return of forests. It is also during this period that we begin to see evidence of ecological succession, the gradual replacement of one plant community by another. The early years were likely dominated by ferns, mosses, and small herbaceous plants. Over time, shrubs and pioneer trees began to appear. Fossil leaf beds show a transition from low-diversity, disturbance-adapted species to more complex assemblages. In some regions, swampy wetlands formed, low-lying areas where water and sediment accumulated, creating stable zones for new plant communities to take root. These wetlands would become biodiversity hotspots in the Paleocene world. Interestingly, this rebound in plant life was not uniform across the globe. Geography, topography, and local climate played major roles in determining the pace and nature of regrowth. Upland areas may have recovered differently from lowlands. Regions closer to the equator likely experienced faster plant turnover due to warmer temperatures and more intense rainfall. But across most of the northern hemisphere, the pattern is clear. By around 58 million years ago, vegetation was no longer clinging to survival. It was expanding, experimenting, and in the process, creating the scaffolding for animal life to follow. One particularly fascinating aspect of this rewilding is the role of plant evolution itself. The extinction event did not just clear space, it may have reshaped the selective pressures on plant traits. In the Paleocene, we begin to see a wider range of leaf forms, seed sizes, and growth strategies. Plants that could adapt to nutrient-poor soils, irregular rainfall, and frequent disturbance had an edge. This was a time of evolutionary innovation, not just ecological recovery. Some researchers argue that this period laid the groundwork for the flowering plant diversity we see today. It was not just a reboot, it was a reprogramming. And yet, despite all this, we still know relatively little about the full range of plant life during this window. Plant fossils are less dramatic than dinosaur bones. They do not draw headlines. But they carry just as much information. Every leaf, every pollen grain, every buried root tells a story about light, temperature, water, and time. And piecing together those stories is one of the most subtle but essential tasks in understanding how life rebounds. There is a haunting beauty in the thought that some of Earth's first post-apocalypse landscapes were covered not by towering forests, but by sprawling mats of mosses, fungal blooms, and unassuming flowering herbs. These were not majestic ecosystems, but they were tenacious, alive, spreading inch by inch, holding the soil, catching the rain, creating shade where there had been none, and giving the next wave of life, whoever and whatever that would be, a chance to walk on something green. So when we ask who the first recolonizers were after the mass extinction, the answer is not heroic. It is humble, it is fungal, it is weedy and fast-growing and quietly essential. Life did not return with a roar, it returned with a sprout. And perhaps the real question is not just who came back first, but how the silent labor of these early plants made the world livable again. Because without them, there would be no food, no forests, and no future migrations. Without them, the rebound would have been barren. So the next time you see a patch of moss reclaiming a sidewalk crack or a weed growing in a burned field, remember, this is how life begins again, not in dominance, but in resilience. And if the Earth ever needs to start over again, it will probably begin the same way, with something small, something green, and something nobody notices, until the whole planet blooms around it. What happens when the planet gets handed to furballs with teeth? Somewhere between 58 and 55 million years ago, the world reached a kind of fragile equilibrium. The skies were lighter, the soil was seeded, vegetation had returned in earnest, and the Earth, after millions of years in post-apocalyptic limbo, was beginning to feel like a habitable planet again. Into this cautious calm, a new class of animal began to spread. Not giant, not ferocious, not particularly impressive at first glance, but clever, adaptable, and quick. The survivors had waited long enough. Now it was time to experiment. And evolution, in its usual quiet chaos, began to favor the small, the nimble, and the dentally ambitious. This was not yet the age of giants. It was the age of rodents. They were not rats. Not exactly. At least not the kind that would eventually creep through sewers and chew wires in human cities. But they were the ancestors, the prototypes. Early members of the order Gliers, rodents and their close relatives, were beginning to diversify across the recovering landscapes of what we now call Eurasia and North America. And though they were tiny, their arrival marks a subtle but revolutionary shift in how life worked. To understand how rodents became so successful, you have to understand what the world had lost. The extinction that ended the Cretaceous had wiped out most of the large-bodied vertebrates, especially those that couldn't hide, burrow, or survive on minimal resources. With the food web reset, there were open niches everywhere. Ecosystems were like abandoned cities, structures still standing, but residents gone. Whoever moved in next had free rein. And rodents, with their generalist diets, fast reproductive cycles, and efficient gnawing machinery, were evolution's squatters. They did not build the city, but they made themselves at home. By the early Paleocene, we begin to find more fossil evidence of multituberculates, a now extinct group that somewhat resembled modern rodents in appearance and behavior. They had specialized teeth for grinding plant material and are thought to have filled some of the same roles that later mice and squirrels would dominate. These multituberculates were already in decline by this point, but they illustrate a key principle: the value of chewing. In a post-extinction world filled with recovering vegetation, seed-bearing plants, and low competition, the ability to process tough food efficiently was a serious advantage. Rodent-like mammals took that principle and ran with it, quite literally. Their limbs suggest an ability to scurry, climb, and navigate complex terrain. Their teeth, especially the ever-growing incisors, were optimized for gnawing, and their brains, modest but effective, gave them the sensory awareness to avoid predators and find food in unstable environments. They were not apex anything, but they didn't need to be. They were background radiation, quiet success stories, small enough to hide, fast enough to move, and numerous enough to matter. What makes this period so interesting is how quickly mammal diversity begins to increase. In North America, fossils from sites like the San Juan Basin show a growing array of small mammals, including early gliers, insectivores, and other placentals, emerging just a few million years after the extinction. In Eurasia, similar patterns appear in the fossil record. There are rodents that dig, rodents that climb, rodents that chew through bark, and rodents that appear to be trying to fill every niche not already claimed by reptiles or birds. This explosion of small mammal forms is sometimes called an adaptive radiation, but that phrase almost feels too clean for what's really happening. This is evolutionary scrambling, a chaotic lottery, and teeth are the ticket. Because the thing about rodents and their ilk is that they do not specialize in domination. They specialize in flexibility. A rodent can survive on seeds, bark, roots, and in some cases even carrion. It can live in a tree or a hole or a patch of grass. It does not need stability. In fact, it thrives on uncertainty. And in the Paleocene, the world was still very uncertain. Climatic fluctuations, tectonic reshuffling, and occasional volcanic activity kept the biosphere just unstable enough to reward opportunists. Rodents were not waiting for equilibrium. They were exploiting the cracks. One example that helps illustrate this adaptive behavior comes from the morphology of rodent teeth. Unlike the molars of carnivores, which are shaped for slicing, or the flat teeth of strict grazers, early rodents developed complex patterns of cusps and ridges that allowed them to process a wide range of plant material. This dental versatility meant that even as plant communities shifted or fragmented, these mammals could still find something to eat. The first real evolutionary advantage, it turns out, was not speed or strength, but the ability to chew almost anything. But even chewing machines need places to hide. And so, in tandem with their dental success, these mammals began to exploit the vertical dimension of ecosystems. Tree-dwelling, or arboreal, forms begin to appear in the fossil record, with adaptations for climbing and gripping. Others took the opposite route, going subterranean. Burrows provided thermal stability, protection from predators, and a place to raise young. The spatial flexibility of these small mammals made them incredibly difficult to dislodge. They weren't just living in the environment, they were occupying every possible microhabitat within it. This rise of small mammals did not happen in isolation. Insects, too, were diversifying, and so were the birds. But mammals were quietly rewriting the rules. For the first time in Earth's history, placental mammals were beginning to take center stage, not as rulers, but as problem solvers, as generalists, as the evolutionary equivalent of duct tape. Useful everywhere, indispensable nowhere, and capable of surviving even when the big players fell. One of the most surprising insights from this time period is how quickly mammal body sizes began to change. Although most were still small, mouse to rat-sized, the average size of mammals in fossil assemblages slowly increases through the late Paleocene. This is the beginning of a trend that will later explode during the Eocene. But for now, it's a whisper, a slow shift upward, not toward giants, but toward options. Evolution was preparing to try new body plans, but it started with safe bets. And safe, in the Paleocene, meant small, furry, and equipped with serious dental equipment. There is something quietly revolutionary about this moment in Earth's history. The dinosaurs had ruled for over 160 million years, and when they vanished, the biosphere could have followed them. Instead, life pivoted, not by rebuilding the same structures, but by trying something new, something smaller, something faster, and in doing so it created a template for resilience that would outlast every future extinction. The rodents of this era are long extinct. Their bones, when we find them, are fragments, a tooth here, a jaw there, tiny echoes of a major transition. But their descendants are everywhere. Every city, every forest, every agricultural field is home to creatures shaped by this early experiment. Squirrels, mice, beavers, porcupines, they are all the legacy of this Paleocene gamble. They are, in a sense, the backup plan, and sometimes the backup plan wins. So what happens when you hand the world to furballs with teeth? You don't get glory, you don't get dominance, you get persistence, adaptation, and a quiet takeover so complete, we barely even notice it anymore. The real haunting question is this: if the world were to end again, who would inherit it next? History suggests it won't be the apex predators, or the clever primates. It will be the ones already watching from the shadows, already nibbling on the edges, already ready. How did the heirs of the dinosaurs learn to fly, then forget again? By the time Earth had shaken off the worst of its post-apocalyptic chaos and settled into the warmer rhythms of the Paleocene-Eocene transition, a new set of creatures had claimed the skies. Gone were the leathery winged pterosaurs that had once glided above Jurassic seas. Gone, too, were the avian-like forms with half-evolved feathers that had struggled for lift among giant predators. What remained, and what now began to diversify with an almost reckless creativity, were birds. Feathers ruled the air, hollow bones floated on thermals. And for a brief, strange stretch of evolutionary time between 55 and 50 million years ago, the sky belonged not just to graceful flyers, but also to beaked monsters that forgot how to fly altogether. This was the avian radiation, an explosion of bird diversity that took place in the quiet shadow of extinction. With pterosaurs out of the picture and much of the biosphere still rebalancing, birds inherited an unusually open field of opportunity. Their ancestors had already made it through the fire. Somehow, a few lineages of feathered bipeds had crossed the extinction boundary with enough genetic diversity and ecological plasticity to begin exploring all the unclaimed aerial, arboreal, and eventually terrestrial niches that had been emptied out. Now, in a recovering world, they could finally breathe and evolve. The story of this radiation is not a single arc, but a braided stream of branching experiments. In Europe, what is now known from fossil-rich sites like Messel reveals a forested environment teeming with early perching birds. forms with zygodactyl feet, grasping claws, and short, maneuverable wings adapted for darting between trees. These were not yet songbirds in the modern sense, but they were likely insectivores and seed-eaters, establishing a now familiar ecological role. One particularly strange genus, Mesalornis, appears to have been a ground-running bird with long legs and short wings, already inching toward flightlessness in certain habitats. Evolution, it turns out, wastes no time questioning its own inventions. Meanwhile, in the southern hemisphere, especially in what is now South America, a very different class of bird was taking shape. Here, some of the earliest large flightless predatory birds began to evolve, later nicknamed terror birds, or forest racids. These were not scavengers or herbivores. They were apex-level carnivores with strong beaks, powerful legs, and, in some cases, skulls nearly the length of a human torso. They could run, they could strike, and though they had wings, they did not fly. These birds had looked at the open ground and made a different choice. Why soar when you can sprint? That choice, between flying and not flying, became one of the defining tensions in avian evolution during this period. In stable, resource-rich environments with few aerial predators, flight was expensive. It took energy. It demanded lightweight skeletons and complex musculature. But if no one was chasing you and the food was on the ground, evolution began to see wings as optional. And so, over and over again, in different continents and unrelated bird lineages, wings shrank. Bones thickened, sternums flattened, and birds that had once taken to the skies began to stomp instead. Yet in the forests and wetlands of the northern continents, the opposite was also unfolding. Birds were getting better at flight, more efficient, more specialized. We begin to see the early diversification of groups that would eventually include owls, waterfowl, and raptors. Some forms adapted for long-distance gliding over open landscapes. Others grew sharp talons and forward-facing eyes, hunting rodents from above. One particularly fascinating lineage, the early relatives of flamingos, seem to have been exploring filter feeding in shallow lagoons long before the familiar pink forms evolved. In short, birds were testing every possible option. But they were not doing it in isolation. Their success was tied to several factors. First, the warming climate of the early Eocene created lush, humid environments across much of the globe, especially in high latitudes. Rainforests reached as far north as modern-day Canada. This created vertical habitat structures, canopies, understories, emergent trees that rewarded aerial agility. Second, the evolutionary vacuum left by the loss of non-avian dinosaurs and pterosaurs meant fewer large predators, at least temporarily. Birds could explore new ecological spaces without constant threat from above. Third, their physiology, endothermic, fast metabolizing, egg-laying, gave them a head start in fast reproduction and environmental flexibility. The fossil record during this time is spotty, as avian bones are delicate and easily destroyed. But where preservation is good, like in the fine oil shales of Messel, we find astonishing details. Imprints of feathers, the outlines of stomach contents, even the shapes of eyes preserved as mineralized pigments. From this, we can begin to reconstruct the behavior, diet, and daily life of these early avian pioneers. One bird was likely nocturnal. Another had seeds in its gut. A third shows evidence of having recently hunted an amphibian. These are not the crude, transitional forms of earlier eras. These are birds, in every modern sense of the word, just ones that haven't yet settled into their final roles. One of the most haunting reminders of how flexible this evolutionary experiment was comes from a group of birds known as Gastornis. These were massive, flightless birds found across Europe and Asia, with thick skulls and powerful beaks. For decades, paleontologists debated whether they were herbivorous or carnivorous. Recent isotopic studies suggest they may have been giant plant eaters, not predators, essentially the Paleocene's answer to a feathered cow. If true, it speaks to just how wide the adaptive range had become. Birds were not just flying, they were filling in for everything that had vanished. And yet, for all their success, this was still an unstable time. Ecosystems were still shifting, climate was volatile, and the evolutionary paths birds were carving were not always permanent. Many of the lineages that flourished during this window would go extinct by the time the Eocene hit its midpoint. Others would evolve into forms we still recognize today: herons, cranes, ducks, but with twists and turns that are still being uncovered. The modern bird tree of life is shaped like a bushfire, rapid, tangled, full of dead ends and survivors that barely made it through. What makes this period so strangely poetic is the duality of the bird experience. On one hand, flight was the great triumph, a tool that had allowed a few feathered dinosaurs to escape extinction and claim the skies. On the other hand, it was also negotiable, optional, a strategy that could be discarded if something better came along. The sky was not sacred. It was just one more place to try living. And so we end up with a world where some birds soared, some perched, and some thundered through forests like two-legged battering rams, each one a footnote in an experiment that never really ended. Even today, birds are constantly testing the boundaries of their own design. Penguins turned into divers, ostriches into runners, parrots into tool users. But it all began here, in the warm, wet shadow of the end Cretaceous cataclysm, with feathers and options. So how did the heirs of the dinosaurs learn to fly, and then forget again? Maybe because evolution never promises progress. It only rewards survival. And sometimes that means giving up the very thing that made you special, because something else, something stranger, works better for now. And the real question, perhaps, is not how birds evolved, but how they keep reminding us that there's no such thing as a finished form. Only adaptations, only experiments, and only a sky that, for now, happens to belong to feathers. Why did the future of mammals begin in the mud? By 50 million years ago, the planet was sweating. Not from fire or fallout anymore, but from heat, humidity, and life. The Paleocene was over. The great extinction's shock waves had finally dulled into background noise, and Earth, left to its own devices, began one of its most lush and riotous ecological experiments yet. Rainforests crept northward, carbon levels rose, oxygen surged, and in low-lying basins, river deltas, and equatorial floodplains across the globe, a new world was fermenting beneath the canopy. A world of shadow, rot, still water, and roots. The wetlands. From Southeast Asia to what would become the American Gulf Coast, these soggy, shaded ecosystems didn't just survive the post-extinction world. They rewrote the rules. And for mammals, still small and largely anonymous in the biological cast, this was the revolution that changed everything. The fossil record for the early Eocene is frustratingly uneven. Yet even through its gaps, a pattern emerges. Around 50 million years ago, the wettest parts of the world became its most creatively chaotic. Swamps, bogs, bayous, and tropical floodplains didn't just host the standard ferns and fish. They began layering, vertically, horizontally, ecologically. Life didn't just occupy the ground anymore. It moved up, into trees, vines, and canopies, and down, into murky waters and root tangles. What had once been a two-dimensional scramble for food became a three-dimensional arms race of agility, diet specialization, and adaptation. And mammals, with their warm blood, sharp senses, and capacity for niche tweaking, took full advantage. Most of the mammals alive during this time were still small by today's standards. Many were less than a meter long. But their bodies were beginning to shift in quiet, important ways. We begin to see more grasping limbs, opposable digits, claws curved not just for digging but for climbing, eyes inching forward on the skull for better depth perception in dappled light, tails elongating for balance, and bones becoming lighter, more flexible, capable of navigating the unstable, tangled world of branches, vines, and half-submerged logs. It's in these wet, overgrown ecosystems that mammalian agility becomes not just a survival tool, but a form of ecological artistry. Fossil sites like the Green River Formation in what is now Wyoming and the Fur Formation in Denmark offer snapshots of this era. Preserved in shale and sediment are impressions of leaves, insects, fish, and the occasional early mammal. One genus, 𝐓𝐈𝐌𝐿𝐄𝐒𝐓𝐀𝐌𝐏𝐒, appears frequently. This small creature was once thought to resemble a hedgehog, but new studies suggest it had a surprisingly agile spinal structure and may have communicated through sound, like modern shrews. It lived in a layered habitat, darting between surface debris and possibly climbing low vegetation. Not a headline grabber, perhaps, but an early hint that mammals were beginning to exploit environmental complexity in a way few other animals could. What made wetlands such effective evolutionary pressure cookers? For one, they were rich in resources, but also unstable. Rainfall was seasonal. Water levels rose and fell. Vegetation exploded and rotted in cycles. That meant animals living in swamps had to be both opportunistic and flexible. You couldn't just evolve one trick. You needed a toolkit. Omnivory helped. So did mobility. And mammals, with their variable teeth and quick reproduction cycles, were unusually good at testing strategies. Some clung to trunks, others leapt. A few scurried through reeds. Over time, this led to a quiet explosion of form. Long-limbed, short-bodied, paddle-tailed, big-eyed. Wetlands were a mammalian gymnasium, and evolution was in full session. Another factor was sound. Dense forests and swamps filter light but carry sound. This favored animals that could hear well and communicate in subtle frequencies. The middle ear bones of many early Eocene mammals show refinement compared to their Paleocene ancestors. This wasn't just random mutation. In a world where you might never see your predator or mate until it was too late, hearing was life. Complex habitats create complex sensory environments, and with them, complex behaviors. By this period, many mammals were developing not just better movement, but better nervous systems to interpret the chaotic world around them. But the real star of this ecological renaissance wasn't any single creature. It was structure. Wetlands layered life in ways the previous epochs never had. Plants began to specialize into canopy, understory, and ground cover. That created corridors of movement for different body plans. The space between roots and waterline became a refuge for semi-aquatic forms. The lower canopy favored gliders and clingers, and above that, light gaps between trees offered brief windows of aerial movement. No other habitat on Earth at the time was this vertically complicated, and for mammals, that was an open invitation to diversify. Not all of this happened gently. Swamps were also dangerous places, full of unstable footing, predatory ambushes, and sudden environmental shifts. But in evolutionary terms, danger often equals opportunity. Creatures that could balance risk and reward, that could adapt their behavior on short timescales, were more likely to thrive. This was not just a world of instinct. It was a world beginning to reward learning. And the plant life? It was going through its own layered transformation. Wetland forests supported an expanding range of flowering plants, many of which co-evolved with the animals that dispersed their seeds or pollinated their blooms. This led to increasingly complex food webs. Mammals that could eat fruit or dig for tubers or harvest insects from bark all found their own niches. Insect life exploded in turn, and with it, so did the animals that fed on them. Curiously, some of the most extreme experiments in body form during this time don't come from the large mammals that would eventually dominate grasslands. They come from small, wetland-adapted species that bent the rules of what a mammal could look like. Elongated ankles, prehensile tails, enlarged olfactory lobes. Some creatures began echoing the features of arboreal marsupials, even though they were from completely different lineages. Convergent evolution, it seems, wastes no time in dense environments. From the fossil record, we also know that these wetland mammals had relatively high rates of turnover. Species appear, diversify, and vanish again in short evolutionary bursts. This suggests highly competitive, unstable ecosystems. Not peaceful Edens, but roiling jungles where change was constant and only the highly flexible could keep up. It was a survival of the clever, the nimble, and the small. A different kind of natural selection. One that didn't always favor brute strength, but navigation skills, dietary adaptability, and stress tolerance. It's also worth noting that while some early mammals used these environments to climb, others took to the water. There are early signs of semi-aquatic forms during this period that hint at the future evolution of full aquatic mammals in later epochs. Webbed feet, denser limb bones, nostrils shifting position. These traits begin as slight drifts in swamp-dwelling populations. The wetlands weren't just vertical, they were amphibious. And for the mammals clever enough to dip a toe in, the eventual payoff would be a return to the oceans themselves. Yet all of this happened quietly. There was no singular wetland mammal that announced the future. No clear hero, just a slow, layered buildup of behaviors and body shapes that, given enough time, would enable mammals to spread into nearly every environment on Earth. The swamp was not the final stage, it was the proving ground, the test chamber where flexibility, perception, and balance were honed. Why did the future of mammals begin in the mud? Because that's where complexity thrives, where cycles of flood and decay force organisms to adapt in 3 dimensions, where life isn't just about eating or being eaten, it's about timing, rhythm, spatial awareness, and resilience. In the silence of a fog-covered marsh, or the flicker of light through a vine-draped canopy, the blueprints of future ecosystems were being written. One grasp, one leap, one tiny heartbeat at a time. And perhaps that's the deeper truth here. The mammals didn't win because they were smarter. Not yet. They won because they could move through chaos without falling apart. The swamp didn't give them superpowers. It gave them puzzles. And the ones who solved them got to keep evolving. And if you trace back far enough from your own nervous system, your own balance and coordination, your own senses tuned for both light and sound, you might find that your body, too, remembers the swamp, a place where mammals learned to climb, to leap, to listen, and to begin imagining more than just survival. So the next time you step into a forest or hear water trickling through tangled roots, remember, this is where the mammals began their ascent, in the quiet, slippery, buzzing depths of the Paleocene's greatest classroom, a world built on mud and motion. When did the story of you begin? And why with something so small and confused? If you could rewind the planet to around 48 million years ago and walk into a forest in what is now central China, you might hear it before you see it. A soft scuttling, a twitch of motion in the canopy, the faintest squeak of something moving through leaves just before dawn. Not quite a squirrel, not quite a shrew, but something with 5 fingers, forward-facing eyes, and a long, balancing tail. Congratulations. You've just had a near brush with one of your earliest evolutionary cousins. And if your expectations were for something majestic, profound, or remotely self-aware, prepare to be underwhelmed. Because the first primates, the very beginning of the lineage that would one day invent philosophy, farming, and satellite internet, were mostly just small, nocturnal animals that were very good at not falling out of trees. It's tempting to look at human evolution like a ladder, straight, noble, inevitable. But the fossil record laughs at ladders. What we actually find again and again is more of a bush, a tangled, half-rotting mess of branches, most of which go nowhere. And somewhere near the root of that bush, in the warm forests of the early Eocene, were the primates. Not human yet, not even close, but beginning to carry some of the basic anatomical quirks that, tens of millions of years later, would make consciousness slightly more complicated than it needed to be. So what were they exactly? Technically, primates are defined by a small set of traits: grasping hands and feet, nails instead of claws, forward-facing eyes that allow for stereoscopic depth perception, and relatively large brains for their body size. These aren't dramatic features. You don't need a PhD in anatomy to recognize the usefulness of grabbing onto branches or seeing in 3 dimensions while leaping through a dark forest. But it turns out, these minor upgrades made a massive difference in how mammals interacted with their world. The first confirmed primates in the fossil record show up during this window between 48 and 45 million years ago. And no, they weren't from Africa, or Europe, or some lost Gondwanan paradise. The earliest crown primates, meaning those clearly on the branch that would eventually include monkeys, apes, and humans, appear in Asia. Fossils like 𝐓𝐈𝐌𝐿𝐄𝐒𝐓𝐀𝐌𝐏𝐒, discovered in China's Hubei province, have given us eerie little snapshots of what our distant ancestors might have been like. This particular creature was tiny, no bigger than a modern mouse. It had long fingers, a short snout, and limb proportions that suggest it could cling and leap. But it wasn't graceful, and it certainly wasn't wise. Most likely it hunted insects in the early morning or late evening, relied on smell and motion detection, and spent a good portion of its short life avoiding snakes, birds, and whatever else was big enough to eat it. It's worth pausing to admit something here. We don't know exactly when primates evolved. There are proto-primate fossils, like the plesiadapiforms, that go back even further into the Paleocene. But these animals were more rodent-like, with weaker vision and less tree-ready anatomy. They're probably close relatives of primates, possibly ancestral, possibly side branches. As usual, the fossil record is too incomplete to say for sure. What we can say is that by the middle of the Eocene, animals with clear primate features were radiating across Asia and North America. Some stayed tiny and nocturnal. Others began experimenting with size, diet, and activity patterns. And all of this happened without anyone inventing tools, fire, or moral ambiguity. Just quiet, unambitious survival in a warm, green world. One of the reasons this period matters is because of what came after. But the temptation to retroactively assign importance to these early primates is a dangerous one. They didn't know they were setting the stage for future empires. They were just adapting to the demands of their habitat. And what the forest demanded, especially in the tangled vertical messes of post-Cretaceous Asia, was balance, vision, and grip. Arboreal life is unforgiving. A missed leap is often a fatal one. So any creature that could more accurately judge distances, adjust its limbs in midair, and hang on with some degree of finesse had a distinct advantage. Primates were not brilliant, they were not beautiful, but they were unusually good at staying in the canopy. This period also marks the quiet beginning of something else, an evolutionary arms race of perception. The eyes of early primates became more forward-facing. That allowed for better depth judgment, a crucial skill when moving between branches. But it also began to shift how the brain processed visual information. Over millions of years, this subtle anatomical change would enable more complex spatial reasoning, faster reaction times, and eventually, more nuanced social interaction. But for now, it just meant these little mammals were slightly less likely to fall. There's also evidence that some early primates began adjusting their activity cycles. While many were nocturnal, the trait wasn't universal. In fact, some groups may have started pushing toward diurnality, being active during the day, in order to avoid competition or take advantage of new ecological niches. This shift would have enormous long-term consequences. Day-active animals rely more on vision than smell, which further favored the development of color perception, pattern recognition, and the visual cortex. Again, none of this was on purpose. It was just evolutionary drift, nudged by light and hunger. But it laid groundwork that would one day allow a descendant species to paint cave walls, map galaxies, and make YouTube documentaries about itself at 2 in the morning. Fossils from this period are rare, but improving. The Messel pit in Germany has yielded exquisitely preserved Eocene mammals, including an early primate named Darwinius massillae. While it was initially hyped as a missing link, the truth, as always, is messier. It's an early primate, yes, but one of many. A branch, not a trunk. Still, the skeleton offers beautiful details. Opposable toes, long fingers, and a body built for climbing and leaping. It is not your great-great-grandmother, but it is, in a way, a ghost of how arboreal life shaped cognition and motion long before sapiens ever nervously stood upright. As always, what survives in the fossil record is a fraction of what once lived. And for tiny primates, the odds of preservation were terrible. Bones that small tend to vanish into soil. So our picture of early primate evolution is like a painting made from 20 pixels. We know the general direction, but we have to guess at most of the detail. Genetic studies suggest that primates may have originated even earlier than the fossil evidence shows, perhaps during the late Cretaceous. If true, that would mean primates coexisted briefly with the last dinosaurs. But again, that's inference, not confirmation. For now, what we know begins here. A few mouse-sized bodies clinging to trees in the post-apocalyptic swamp world of the early Eocene. What's fascinating is how slow everything was. The jump from these first primates to the earliest monkeys and apes took tens of millions of years. There was no rush, no teleology, just endless micro-adaptations stacking on top of each other like sediment in a bog. And with each generation, the eyes grew more precise, the fingers more articulate, the brain slightly more sensitive to pattern and time. It would be a very long time before any of this resembled what we call thought. But the seeds were here, buried in trees, waiting. So no, the first primates were not impressive. They didn't paint anything, they didn't form societies, they didn't even look particularly interesting. But in the quiet middle chapters of mammalian history, they were doing something extraordinary, building complexity inside their bodies, generation by generation, with no script and no guarantee of success. And that's probably more impressive than we give them credit for. The haunting question, of course, is this. If a nervous, half-blind tree dweller could eventually give rise to a species capable of streaming itself into satellites, What else right now is evolving quietly in the dark? What other lineage is one grip, one leap, one slightly better sense of depth perception away from becoming the next unlikely chapter in Earth's story? The future never looks like much when it's still clinging to bark. There are certain moments in Earth's story where nature seems to lean into nostalgia, as if some forgotten impulse deep in the genetic soup remembers what it was like to be large, loud, and impossible to ignore. This was one of those moments. Not long after the fall of the reptiles, in a world still reshaping itself from ash and silence, evolution tried something audacious. It tried to bring back the giants. Not scaled this time, not with teeth the size of bananas or tails that could flatten forests. These new giants were built out of fur, bone, and calories. Some looked like enormous rhinos, others like prehistoric tapirs with horns that didn't make anatomical sense. They weren't subtle, but they were, in their own way, a sign that the planet was healing. Roughly 45 million years ago, the land masses of North America and Eurasia were buzzing with evolutionary energy. Forests still blanketed much of the continents. The grasses that would later reshape everything hadn't yet taken over. Instead, it was a world of ferns, flowering plants, and trees thick enough to lose a parade of elephants in. But where there were leaves, there were mouths. And where there were mouths, evolution found a way to make them much bigger. Enter the Brontotheres. Imagine a rhino. Now stretch it, bulk it up, give it a comically oversized head with a Y-shaped horn structure that probably wasn't very good at anything except confusing paleontologists. These creatures, also called titanotheres, were part of a family of perissodactyls, odd-toed ungulates, that would dominate the northern continents during the Eocene. They could grow up to 4 meters in length, and some weighed more than 2 metric tons. Not bad for an evolutionary experiment that started with tiny hoofed creatures picking their way through ancient underbrush. But the Brontotheres were just one act in a larger trend. In the same span of time, strange and equally massive herbivores were stomping around with names like Uintatherium, a beast with a vaguely hippo-like body, a head studded with horn-like protrusions, and prominent saber-like tusks hanging from its jaw. It looked like someone let a child redesign a mammal without supervision. Its skull alone measured over 60 centimeters. Its brain, humorously, was not that impressive. If intelligence were a requirement for survival at the time, these creatures would have gone extinct by lunchtime. And yet they thrived, because what mattered wasn't intellect. It was digestion. To survive in this lush but chemically tricky world of tough leaves, fibrous stems, and slow-growing canopy plants, you needed guts, literally. Massive fermentation chambers, complex stomachs, and jaw mechanics that could mash your way through an entire tree if needed. These herbivores weren't fast, they weren't bright, but they were efficient walking fermentation tanks. And in ecosystems without large grasslands or fast-moving predators, that was more than enough. The energy dynamics of this period were unique. Plants had bounced back in full force after the cataclysm that ended the Cretaceous. Atmospheric carbon dioxide was higher than today. Temperatures were warm and fairly stable. Polar regions, though cooling, were still ice-free. This warmth allowed lush forests to stretch nearly to the poles, and with them came biomass, lots of it. The food web had room again for massive bodies, slow lives, and animals that were essentially nature's bulldozers. For a brief chapter, size made a comeback. But gigantism comes at a cost. A bigger body means slower reproduction, greater caloric needs, and more vulnerability to ecological shifts. It's a high-risk, high-reward strategy, fine in stable times, catastrophic in a crisis. Still, for these several million years, the gamble paid off. The fossil record shows that some of these lineages expanded rapidly in range and variety, appearing in what's now Wyoming, Mongolia, Kazakhstan, and Central Europe. Their footprints can still be traced in ancient lake beds and sediment layers where prehistoric rivers once ran thick with silt and insect buzz. Their bones show more than size. They show stress. Thickened joints, bone remodeling, and arthritic wear patterns suggest these giants weren't just heavy, they were under constant mechanical strain. Their lives were slow, growth rates were long, injuries took time to heal, but they carried on, reshaping their environments by simply existing. When a 2-ton mammal wanders through a forest, It leaves trails. When it feeds, it snaps branches, tramples saplings, and opens space for sunlight to hit the forest floor. These creatures weren't just animals. They were ecological architects. Their emergence also hints at an important evolutionary principle: convergence. When nature finds a strategy that works, it often tries it again. The large-bodied herbivore is a recurring character across deep time. Dinosaurs did it. Mammals did it. Even some reptiles in the Permian tried a version of it. And every time the solution is slightly different, but the role is familiar: a big, slow, plant-eating creature that sets the tempo of its ecosystem. We often think of the age of mammals as something that led directly and efficiently to us. But this period reminds us that evolution is rarely in a hurry, and it doesn't aim for intelligence, just persistence. The world of 40 million years ago was not a halfway point on the road to sapiens. It was a complete story in itself. These animals weren't primitive. They were adapted, perfectly suited for a world that, to us, would feel like a greenhouse dream. Steamy, green, and filled with sounds we'll never hear again. And then, of course, they vanished. Not all at once, not dramatically, but gradually. As climates shifted, as forests began to recede in places, as new competitors emerged, the giants began to falter. The last Brontotheres disappeared around 34 million years ago. 𝐓𝐈𝐌𝐿𝐿 didn't fare much better. Their fossils became more sparse, their diversity narrowed, and eventually they were gone, leaving behind teeth, bones, and more questions than answers. Why did they fail? Was it cooling climates, the rise of more efficient grazers, the beginnings of competition with new predators? The data doesn't hand us a neat answer. Paleontology rarely does. All we know is that size, while impressive, isn't invincible. Sometimes the very traits that let you dominate in one era become your undoing in the next. Still, for a time, they ruled. Not with speed or smarts, but with mass and presence. They reminded the planet what it felt like to shake under the weight of living giants. And in doing so, they carved a brief but unforgettable chapter into the book of life. So next time you picture the past, try to hold this image. Not just sharp-fanged predators or cunning proto-primates, but a forest world rumbling with the slow thunder of giant mammals. Creatures that tried for a little while to wear the crown of size once held by the dinosaurs. And ask yourself, if evolution keeps bringing giants back, is it because the planet needs them, or because it just misses them? If you could walk the forests of what is now North America, or the wide floodplains of Eocene Europe around 40 million years ago, you would not find lions. No wolves, no big cats, and certainly nothing quite like the predators we know today. But you would not be safe. The world was, for the first time in the age of mammals, home to creatures that did not graze, did not chew leaves, and did not retreat into the canopy. Instead, they hunted, they smelled, they tore, they killed, and they were mammals. The first real wave of mammalian predators was not built like the ones we know now, and frankly, most of them were odd. But they were good enough. For tens of millions of years, they ruled without rival, and then they disappeared. When paleontologists trace the fossil layers of predator evolution after the Great Extinction, one group shows up over and over again: the creodonts. Not to be confused with modern-day carnivores, the creodonts were a separate and now extinct order of meat-eating mammals that filled many of the same roles we associate with wolves, hyenas, and big cats today. The name creodont comes from Greek, kreos, meaning flesh, and odous, meaning tooth, a name that cuts right to the point. These were flesh-toothed mammals, and in the late Eocene, they were everywhere. The largest of them could reach the size of a small bear, like Hyenodon, a predator with a long skull, slicing teeth, and a jaw hinge that gave it a devastating bite. Its name is misleading. Hyenodon was not a hyena, it was not a dog, it was not anything we still have around today. And yet, it was one of the most successful carnivores of its time, roaming across what is now North America, Asia, and Europe for millions of years. Other creodonts, like Sarcastodon, grew even larger, up to nearly 1,000 kilograms, some estimates suggest, and may have hunted or scavenged early giant herbivores in open forest and wetland zones. They did not leap from trees. They did not stalk prey silently like modern cats. They probably moved more like big scavenging bears, with massive heads and a sense of smell that led them to death. Their closest competitors were not cats or canids, because those had not evolved yet. The world before 40 million years ago had not yet invented the modern predator toolkit. And so, evolution tried other options. Many creodonts had enlarged slicing premolars and molars, what are called carnassial teeth, ideal for cutting through flesh. But their brain cases were small. Their hearing and vision may not have been exceptional. They were not the sleek, fast, precision killers we know today. They were more like blunt instruments of meat recycling, and for a long time, that was enough. Meanwhile, a different lineage of predators was quietly forming. These were the earliest members of the order Carnivora, the one that would eventually give rise to cats, dogs, bears, weasels, and even seals. But in the early stages, these ancestors were small, unassuming, and often omnivorous. Think, raccoon-sized generalists with flexible diets and sharp teeth. They had not yet taken over. For tens of millions of years, they lived in the ecological margins, dwarfed in size and outcompeted in bite force by the larger creodonts. It is one of those strange moments in evolutionary history where the eventual winners were the weirdos on the sidelines. For now, the creodonts had the crown. What made the creodonts work was not elegance, but timing. The world between 40 and 35 million years ago was still warm, forested, and full of mammalian prey. Small herbivores, climbing browsers, and early hoofed mammals formed the base of a growing food pyramid, and the top slot was wide open. Without birds of prey in those habitats, without reptilian predators of size, and with no competition from big cats or saber-tooths yet, these shaggy-jawed, slow-brained meat machines had the field to themselves. But evolution is a game of trade-offs, and over time, their limitations started to matter. Creodonts had a slow reproductive rate, long gestation, and may have lacked the behavioral flexibility that defines later carnivores. Their limb structure was not optimized for running or pouncing, and perhaps most critically, their brains did not seem to grow in tandem with the increasing complexity of the ecosystems they ruled. Over the next few million years, something shifted. Slowly, quietly, the true carnivores, the early miacids and vivarivids, began to expand. They were smaller, faster, and more adaptive. They could climb, they could scavenge, and eventually, they could hunt. The age of mammal predators was about to undergo a coup. But during this window, when creodonts still reigned, Earth was testing what it meant to be a killer. One of the more fascinating adaptations to emerge in this period was not a bigger body or stronger jaw, but a better nose. Many of these early predators seem to have relied heavily on scent rather than sight. Their nasal cavities were large. Their olfactory bulbs, where smell is processed in the brain, were often more developed than those of their prey. The battle between predator and herbivore may not have looked like a chase across the plains, but rather a slow, quiet tracking through ancient forest corridors. The kill would come not from stealth or speed, but persistence. Scavenging was also a key part of the equation. Some of these carnivores may have been more like hyenas than tigers, bone crackers that followed the trail of rot. That strategy makes sense in a post-extinction world where carcasses were plentiful and energy was precious. We tend to think of predators as majestic, elegant creatures. But the truth is, evolution doesn't care about style points. It cares about who eats. And the first mammals to take on the role of apex predators may have done so without elegance, but with relentless biological efficiency. This is also the first time in mammalian history when killing became a profession. Before this, many mammals were opportunistic feeders, flexible generalists, or hiders and foragers. Now there were animals that made a living exclusively by tracking, killing, and consuming other vertebrates. It changed the structure of ecosystems. It forced prey species to adapt, with better hearing, faster reflexes, or more cryptic behavior. It created, for the first time in the Cenozoic, what ecologists call a trophic cascade. Energy flowed upward, from plants to herbivores to meat, and the ones at the top were, finally, mammals. As we look back at this period, it's easy to think of these predators as failures. After all, they're gone. The creodonts vanished sometime in the early Miocene, after dominating for tens of millions of years. Their evolutionary experiment ended. But from a paleontological perspective, lasting that long is not failure. its success with an expiration date. The world changed, the climate shifted, new competitors rose, the more behaviorally flexible, socially intelligent, and agile carnivores eventually took over. But without these first waves of mammalian killers, the stage might not have been set. And the question that lingers is, what might it have looked like if they had lasted, if brain size had increased, if adaptability had kicked in? Could we live on a planet today where the top predators are not cats, not dogs, but something far more ancient, descendants of meat-toothed beasts with slow brains and huge jaws? Or was the whole creodont story simply a placeholder, an evolutionary beta test before version 2.0? It's hard to say, because we don't get to rewind. We only get to dig up the bones and guess. And sometimes the bones suggest that the first mammal predators weren't graceful, weren't clever, and weren't efficient in any modern sense. But they were alive. And for a while, they were the kings. What does it take to end a tropical world? For tens of millions of years after the dinosaurs fell, Earth leaned into its greenhouse mood. Palm forests hugged the poles. Crocodiles swam in what is now Wyoming. And for a long, blissfully humid moment in geological time, it seemed like jungles might just win. But sometime around 35 million years ago, the green dream began to die, and it did not go quietly. It begins, as many planetary tragedies do, with a slow drift no one notices at first. By the time we reach the end of the Eocene epoch, Earth's atmosphere is already flirting with instability. The continents have been quietly drifting toward confrontation. Antarctica, once lush with forests, is now inching toward isolation at the bottom of the globe. And like a switch being flipped on a planetary scale, something changes. Ocean currents shift, moisture patterns break, and then, just like that, snow begins to fall where palm trees once stood. What followed was one of the most dramatic climate shifts in the past 100 million years. The Eocene-Oligocene transition was not a single event. It was a cascade, a climate cliff that shattered ecosystems, rewrote evolutionary scripts, and reintroduced something the planet hadn't dealt with in a long time: serious, sustained cold. Let's be clear, this wasn't just a chilly breeze rustling some trees. This was the birth of a full-scale icehouse world. For the first time in over 30 million years, Antarctica froze. Permanent ice sheets formed at the poles. Sea levels fell. Global temperatures dropped by an estimated 4 to 5 degrees Celsius, and that slight numerical dip was enough to push entire ecosystems over the edge. In the fossil record, we see the signs everywhere. Across Europe, North America, Asia, and Africa, lush subtropical forests thin out and vanish. The diversity of plants collapses. Insect populations nosedive. Wet, jungle-rich habitats are replaced by open woodlands and scrub. And the rain, that essential ingredient for all things leafy and lush, becomes erratic, weaker, and in some regions, disappears entirely. Antarctica, once green and swampy, becomes a continent encased in white. Sediment cores from the Southern Ocean reveal the rapid onset of glaciation. Tiny shelled organisms that drift in the water, foraminifera, record the changing chemistry of the oceans like microscopic black boxes. Their shells tell us the water got colder, denser, and less friendly to life. What caused all this? The leading suspect remains Antarctica's breakup with Australia and South America. As those continents drifted apart, a new ocean passage opened up, the Drake Passage. This allowed the formation of the Antarctic Circumpolar Current, a looping, cold water conveyor belt that effectively thermally isolated Antarctica. Think of it like giving the continent its own personal air conditioning unit, one that never turns off. And once the ice began to build, it triggered feedback loops that only made things worse. Ice reflects sunlight, which cools the surface, which forms more ice. Less evaporation means fewer clouds, which means less greenhouse trapping. Volcanism may have briefly tried to fight back with CO2, but the tide had turned. The Earth was committed. Tropical paradise had been evicted by the first real glacial landlord in millions of years. So what happened to the species that had thrived under the old, warm regime? Many of them simply didn't make it. This extinction pulse wasn't as dramatic as the asteroid that ended the Cretaceous, but it was brutal in its own quiet way. lineages of warm-adapted plants, amphibians, and reptiles disappeared. The rainforests of North America, once home to ferns, palms, and giant salamanders, gave way to more open, drier ecosystems. The diversity of mammals took a hit too, particularly those adapted to dense forest habitats. Even the oceans weren't safe. The cooling climate altered ocean stratification, disrupting nutrient cycling. Deep-sea species vanished. Coral reefs declined. And as more water was locked up in ice, sea levels fell, exposing shallow coastal ecosystems to collapse. For creatures that had bet their evolutionary chips on warmth, the rules had changed. But like every story in Earth's past, loss came with opportunity. The cooling, drying, and opening up of the landscape created new arenas for evolutionary innovation. Animals adapted to open habitats, to longer migrations, to grazing rather than browsing, began to rise. Grasses had already been experimenting with evolution in the background, and now they began quietly spreading. Forests were no longer dominant. They were becoming fragments, interrupted patches in a landscape increasingly shaped by wind, dust, and drought. For the first time in ages, life had to learn how to survive without a canopy. The jungles did not vanish everywhere. In equatorial regions and protected basins, patches of dense forest clung on, but the dominance was broken. The age of the eternal jungle, the post-dinosaur greenhouse utopia, was officially over. Earth had turned a page, and the next chapters would be written under colder skies. In the fossil beds of Central Asia and North America, we begin to see new forms of plant life taking hold. Grasses appear more frequently, woody shrubs spread, trees adapt to frost, and animals start showing teeth patterns and limb structures suited for running, digging, or chewing tougher, drier plant matter. But through it all, what's perhaps most remarkable is just how fast it happened. Geological records suggest the major temperature drop around this transition may have unfolded in less than 500,000 years. In planetary terms, that's almost instant. Imagine a rainforest world becoming a frost-bitten mosaic of scrublands in what would be, to evolution, the blink of an eye. And in the middle of all this, life did what it always does. It adapted, radiated, collapsed again, then adapted once more. No committee planned the outcome. No organism knew what was coming. Evolution just stumbled forward, through extinctions and bottlenecks and accidental successes, into a new planetary story. If there is one thing the Eocene-Oligocene transition reminds us of, it's this. Climate is not a background character in the story of life. It is the stage, the script, and sometimes the director. When the air cools, the water shifts, and the ice returns, entire evolutionary trajectories can rise or fall based on who can cope and who can't. It also reminds us that even paradise has an expiration date. For tens of millions of years, Earth was a greenhouse. For tens of millions of years, forests ruled. But all it took was a few drifting continents, a small tweak in ocean currents, and the subtle feedback loops of ice and albedo to bring the age of the jungle to a frozen end. And yet, here we are. Born of those survivors, descendants of the lineages that somehow made it through the frost, the fragmentation, the failure of the canopy. You, listening to this now, are only here because something with lungs, a stomach, and perhaps a very bewildered brain managed to persist after the trees fell quiet. And so the question lingers. If a jungle can vanish in 500,000 years, and ice can bloom on a once tropical pole, and entire forests can fall to silence, what part of the planet's story are we currently misreading? And would we even notice the climate changing again until the trees go quiet once more? There are revolutions in Earth's history that are easy to spot. An asteroid slams into the planet, a supervolcano darkens the skies, an ice sheet creeps down from the poles. But others take their time. They do not explode, they spread. Quietly, stubbornly, invisibly at first. Until one day you look around and realize the entire world has been rewritten by a leaf. This is one of those stories. The story of grass. A family of plants so successful, so unassuming, and so evolutionarily aggressive that it didn't just carpet the earth, it rewired life itself, including the part of life that would one day start domesticating it. and writing documentaries about it. But long before any ape figured out how to mow a lawn or plant a field, grasses were creeping across Africa and Eurasia, preparing to flip the rules of who lives, who dies, and who gets to chew for a living. Around 33 million years ago, Earth was in flux. The warmth of the Eocene was over. Antarctica had frozen, forests were retreating, and global carbon dioxide levels were slowly declining, not yet catastrophic, but enough to shift the balance. The air was no longer thick and heavy with greenhouse gases. With cooler, drier conditions expanding in the mid-latitudes, the old giants of the jungle, towering hardwoods and dense canopy dwellers, began losing ground. In their place came something lower, leaner, more modular, and endlessly adaptable: grass, or more precisely, the Poaceae family, a botanical lineage that had been lurking in the underbrush for tens of millions of years but now, finally, had the upper photosynthetic hand. To understand why this moment mattered, you have to think like a plant. Most of the world's flora at the time used what's known as C3 photosynthesis, a process optimized for wetter, cooler environments with plentiful carbon dioxide. But as conditions dried and CO2 levels dropped, that mechanism became increasingly inefficient. Grasses, however, had a secret weapon, a different metabolic pathway called C4 photosynthesis. It was turbocharged, more water efficient, more nitrogen efficient, and able to keep running even under intense sunlight and heat. While the precise origin of C4 photosynthesis is still debated, it seems to have emerged in certain grasses around this time, likely in open, seasonally dry environments in what is now Africa or the Indian subcontinent. Once that genetic switch flipped, the rest was chlorophyll-soaked destiny. C4 grasses began to radiate outward, outcompeting their C3 cousins in areas that were once dominated by shrubs and forest edge species. Their architecture helped too. Unlike trees that commit to large, slow-growing structures, grasses build fast and recover faster. Burn them, graze them, trample them, they bounce back. Most of their vital growth points are at or below the soil surface, and unlike many plants, they seem to relish disturbance. Fire? They love it. Grazers? They depend on them. In fact, grasses and grazers evolved together into one of the most brutally effective feedback loops in natural history. Each benefited from the other's violence. By 29 to 28 million years ago, vast areas of Africa and Eurasia had transformed. What had once been a patchwork of woodlands and seasonal forests was becoming something new, something open, bright, dry, and filled with waving blades and shallow roots. The age of the forest floor was giving way to the age of the grassland, and the implications for animal life were enormous, not just because the habitat changed, but because the rules of eating changed with it. Grass is terrible food. It's tough, it's fibrous, it's loaded with silica, which wears down teeth like sandpaper, and it's low in calories compared to fruits, seeds, or meat. For an animal to survive on grass, it needs serious hardware, specialized teeth, enormous guts, or both, which means the spread of grass triggered an evolutionary arms race among herbivores. Only those who could chew longer, digest better, or bulk up bigger would make it. High-crowned teeth, chambered stomachs, long legs for moving between patches. Suddenly, being huge and heavily jawed wasn't just a luxury, it was a requirement. This new ecosystem dynamic also reshaped the energy flow. In forests, most of the productivity is locked up in wood, tall trees and permanent biomass that decomposes slowly. But in grasslands, productivity is fast and cyclical. Grasses grow quickly, die quickly, and fuel massive populations of herbivores that in turn feed predators, scavengers, and entire microbial communities in the soil. Everything speeds up, everything spreads out, and the landscape itself begins to change. Grasslands stabilize soil, reflect more sunlight, and even help pump water into the atmosphere through evapotranspiration. They are not just passive biomes, they engineer their own weather. Of course, none of this was immediate. Evolution is not a headline, it is a pattern, repeated and tweaked across millions of breeding cycles. But by the late Oligocene, around 28 million years ago, it was clear the world had shifted. Fossil pollen records show an uptick in grass species across multiple continents. Isotopic analysis of fossil teeth reveals a shift in diet among herbivores towards C4 plants. And the bones themselves tell the story of bodies adapting to a different pace of life. longer limbs, different ankle joints, heavier jaw musculature. The forest dwellers were being replaced by runners, grazers, and chewers. A biome had changed, and with it, the animals who served it. It's important to note that not all grasslands looked the same. These were not the endless prairies of modern imagination. Early grass-dominated ecosystems were patchy, mosaic-like, and often interrupted by shrubby areas, seasonal wetlands, and remnant forest groves. But the trend was clear. Openness was increasing. The vertical complexity of old jungle systems was flattening out into horizontal sprawl. Light reached the ground more often. Wind became a shaping force. And fires began their long, crackling dance with vegetation, both natural and later, much later, human. And this is where it gets philosophical. Because this humble plant family, with no brain, no ambition, and no agenda, was in the process of changing the entire trajectory of Earth's evolutionary story, not with strength or speed or cunning, but with persistence, with the ability to thrive on what others ignored. Grass did not just outcompete, it rewrote the rules of survival. It created the niche that would make room for everything from thundering herds to quiet burrowers, to one very odd lineage of apes that would eventually stop climbing trees and start mowing fields. But we're not there yet. In this period, between 33 and 28 million years ago, the world was still figuring out what this new grassy reality meant. Some species thrived, others vanished. Some biomes remained forested oases, holding on to the past. But the trend was clear. A plant had risen, a biome had shifted, and Earth had been quietly conquered by something you can step on without noticing. So the next time you walk through a field or see a savanna on a postcard, remember, you're looking at one of the most successful invasions in the history of life. Not by a predator, not by a disease, but by a photosynthetic strategy, one that flipped the carbon equation, challenged the digestive limits of mammals, and laid the literal groundwork for everything that would come after, including you. And the haunting question, of course, is this. If a single family of grasses could transform the biosphere without making a sound, what else are we overlooking? Mammal life were enormous, not just because the habitat changed, but because the rules of eating changed with it. Grass is terrible food. It's tough, it's fibrous, it's loaded with silica, which wears down teeth like sandpaper, and it's low in calories compared to fruits, seeds, or meat. For an animal to survive on grass, it needs serious hardware, specialized teeth, enormous guts, or both. Which means the spread of grass triggered an evolutionary arms race among herbivores. Only those who could chew longer, digest better, or bulk up bigger would make it. High-crowned teeth, chambered stomachs, long legs for moving between patches. Suddenly, being huge and heavily jawed wasn't just a luxury, it was a requirement. What did stomachs have to do with world domination? It's not the question most people ask when staring at a cow, or a deer, or the quiet, judgy face of a camel. But somewhere between 28 and 24 million years ago, evolution answered with a quiet biological hack. If you want to thrive in a world of hard-to-digest food, don't change the food, change your gut. The result was the rise of the ruminants, and with them, a dietary revolution so efficient, so deceptively simple, that it would eventually shape everything from human agriculture to planetary carbon cycles. This was not a loud takeover. There were no fangs, no talons, no trumpeting conquests, just stomachs, doing weird things, very efficiently. To understand the origins of the Ruminant Empire, we have to step into a world that was, in many ways, unfamiliar. By the time we reached 28 million years ago, much of Earth's tropical abundance had already been muted by cooling climates and regional drying events. Antarctica was frozen now. Ocean circulation patterns had shifted. Forests still existed, but they were breaking apart, fragmenting under the pressure of changing rainfall, seasonal instability, and slowly encroaching grassland biomes. The environment was no longer a buffet of soft fruits and lush greenery. If you were an herbivore, your future depended on your ability to extract energy from things that most animals couldn't digest, like dry leaves, bark, twigs, or most importantly, grass, which is not the generous snack it appears to be. The mammals we call ruminants, deer, cattle, sheep, giraffes, antelopes, and their ancient ancestors, didn't just eat differently. They digested differently. Deep in the gut, in chambers specialized for microbial work, food wasn't just broken down, it was fermented. Bacteria did what the mammals themselves couldn't: break cellulose into usable energy. It's a microbial outsourcing contract that persists to this day. These foregut fermenters became walking compost bins, their digestive strategy not based on speed, but on time. Time to chew, time to regurgitate, time to chew again, and time to let their microbial partners do the dirty work. The technical term is rumination, but for millions of years, it just meant survival. While other herbivores were locked in an arms race of tooth shape and chewing mechanics, these mammals sidestepped the game with microbial allies and a stomach that became an entire ecosystem unto itself. The result was a body plan optimized not for hunting or climbing, but for energy efficiency. Long limbs for ranging, large guts for fermenting, and jaws built not to slice but to grind. The ecosystem didn't just adapt to them, they helped create new ones by the very way they grazed, fertilized, and recycled nutrients through digestion. What's astonishing is how early this transformation took root. In parts of Asia and Africa during the late Oligocene, fossil evidence shows a growing diversity of artiodactyls, the even-toed ungulates, branching off into more specialized herbivores. Some were proto-camels with odd teeth and desert-ready physiology. Others had already begun experimenting with multi-chambered stomachs and grazing behaviors. In ancient riverbeds, we find their tracks. In sediment cores, their methane signatures. And in the wear patterns on fossil teeth, a story of animals eating differently than the browsers and jungle dwellers before them. This was not yet the age of farms or fences. No human hand was guiding this. But the digestive physiology we rely on today, for dairy, meat, wool, and cultural identity, was already quietly evolving beneath the canopy and across the plains. It would take tens of millions of years for that evolution to intersect with ours. But by the late Oligocene, the stage was set. The ruminants weren't the biggest, they weren't the strongest, but they had something better: metabolic elegance. It's easy to overlook just how radical this digestive system is. The ruminant stomach isn't one organ, it's four: the rumen, reticulum, omasum, and abomasum, each chamber with its own purpose. The rumen is a fermentation vat, the reticulum sorts particles, the omasum absorbs water and minerals, the abomasum finally resembles a typical stomach. But the genius of this design is in its cyclical rhythm. Food is swallowed, fermented, regurgitated, chewed again, fermented more. It's a loop of recycling, refinement, and patient energy extraction. If there's an evolutionary metaphor in all this, it's that sometimes the best strategy is to slow down, chew your problems twice, and let bacteria do the heavy lifting. And this design isn't just about nutrition, it's about ecological dominance. Ruminants could colonize places that other herbivores couldn't: dry grasslands, seasonal forests, alpine meadows. They could survive on low-protein diets, turn marginal lands into viable habitats, and expand across continents without waiting for the perfect conditions. Their stomachs were, in essence, a mobile processing unit for tough vegetation, which meant the more the world tilted toward drier, tougher plant life, the more they thrived. What makes this even more quietly impressive is that no central authority coordinated it. No single mutation invented the four-chambered stomach overnight. Like all great biological innovations, it was piecemeal, gradual, a messy sequence of tweaks, pressures, and microbial partnerships that turned one group of unassuming mammals into ecosystem engineers. And while the big names of evolution tend to be jaws, claws, and brains, in this case, it was digestion that won. By 24 million years ago, the ruminant lineage had diversified across Asia and Africa. They were still evolving, still adapting, but the blueprint was in place. And from that blueprint would eventually emerge giraffes, antelopes, gazelles, and domestic cattle, animals that would redefine the landscape, the human diet, and eventually the global carbon budget. Not bad for creatures whose superpower is chewing twice. So what does a stomach have to do with world domination? Maybe everything. Because in a world that was becoming harder, drier, and nutritionally poorer, the most powerful evolutionary tool wasn't speed or size or even intelligence. It was fermentation, microbes, and the long, patient art of digesting the indigestible. That, and having the evolutionary humility to chew your food more than once. And just like that, the next chapter of the mammal story had a new hero. Not a predator, not a primate, but a ruminant, quietly belching its way into history. What happens when brains meet branches? It's not a riddle, it's a real moment in Earth history. Somewhere between 24 and 20 million years ago, something ancient, nervous, and very experimental looked out from a tropical canopy and hesitated. It had hands, not paws. It had a brain, not a reflex. It had eyes set forward and a sense that something, maybe everything, was watching back. And if that sounds like the beginning of your story, it is. But we're not there yet. These weren't humans. They weren't even apes. These were monkeys. And as underwhelming as that might sound, the expansion of early monkeys across Africa and Eurasia marked one of the strangest, smartest, and most significant biological takeovers of the entire Cenozoic. Not because they were big, not because they were fast, but because, for the first time in Earth's long evolutionary theater, some small-bodied mammals started winning with cleverness. To understand how monkeys took the trees, you first have to understand what it means to live in them. Arboreal life is not a peaceful jungle scene. It is a full-body chess match played over air. Every leap has consequences. Every branch is a bet. In this leafy game, claws and instinct only get you so far. What helps more? Depth perception, balance, dexterity, and perhaps most critically, memory. Monkeys, as it turns out, were not just another set of mammals with tree-climbing skills. They were part of a very select lineage of primates that started adapting their entire sensory world for an aerial three-dimensional maze. Their shoulders began to rotate differently. Their hands started grasping in ways that other mammals could not replicate. And their vision, forward-facing and stereoscopic, let them map out trajectories in midair. This wasn't random mutation. It was relentless feedback from gravity itself. And gravity, as usual, was not kind to the slow learners. By around 23 million years ago, fossil evidence from Africa and parts of Arabia begins to show a burst of diversity in what we call anthropoids, the group that includes monkeys, apes, and eventually, us. But in this part of the story, apes don't exist yet. And the monkeys aren't exactly winning beauty contests. Most are small, fast, long-tailed, and built for the trees. Some look like they were designed by committee. Others seem like evolutionary drafts. But one thing they all had in common, they stuck with each other. Unlike most mammals, monkeys are social. Deeply, confusingly social. And while that might sound cute, it's really not. Sociality in primates is less about hugging and more about strategizing. Who can you trust? Who just stole your food? Who's going to groom you today and betray you tomorrow? These are not questions a squirrel asks, but monkeys do. And that meant that somewhere in the tangled logic of group living, primate brains started changing shape. Now we do have to be careful here. Brain size alone is not a measure of intelligence. But when it comes to monkeys of this era, we start to see something unusual. Compared to other mammals of similar body size, monkeys were carrying a bit more neural tissue upstairs than expected. They weren't writing poetry, but they were navigating complex group hierarchies, coordinating movement through forest canopies, and, most strangely of all, beginning to teach. Not formally, of course, but observational learning, imitation, and the slow transfer of behavior through generations began to creep into the evolutionary record. In some sense, monkeys were becoming cultural. By 22 million years ago, monkey populations had begun expanding beyond Africa. Fossils found in Pakistan and parts of India show that some species had already made the trek across what is now the Arabian Peninsula and into Eurasia. This is not a small thing. Dispersal across continents means adapting to new trees, new food sources, and new predators. It also meant recalibrating social behaviors to new environmental pressures. You're not just climbing anymore, you're competing. And monkeys, despite their size, were astonishingly good at competition. Not through brute force, but through numbers, coordination, and memory. The forest was no longer a neutral place. It was being organized, layer by layer, by brains that could plan ahead. What did these early monkeys eat? Almost everything they could get their tiny hands on. Fruits, leaves, insects, flowers, gum, bark, seeds. They weren't picky, but more importantly, they were flexible. Diets could shift with the season. Territories could adapt. In evolutionary terms, this flexibility is golden. Specialists go extinct when their niche collapses. Generalists, especially ones with hands, tend to survive. And the monkeys of this era were generalists with ambition. Fossil evidence suggests that many of these early species were active during the day. This might not sound remarkable, but it's a key turning point. Earlier primates, including some of the most ancient proto-monkeys, were nocturnal. Shifting to diurnal life changes everything. Your visual system becomes optimized for color and contrast. Communication becomes more visible. Social signals, facial expressions, gestures, posture start to matter. And slowly, the forest starts to feel a bit more observed. This is where the creeping sense of self-awareness may begin. Not consciousness in the modern human sense, but awareness of being seen, judged, tracked, remembered. Monkeys, as simple as they might seem, were pioneers of a new kind of mental space, one where social context was everything. It wasn't all upside. Arboreal life is dangerous, and not all monkey species made it. Some fossils disappear as quickly as they appear. But the pattern is clear. Over these 4 million years, the number of anthropoid species expands, and their ecological roles multiply. Some get smaller, others get bigger. Some remain exclusively tree-bound. Others begin flirting with the ground. But across the board, monkeys were mastering something no other mammal had attempted: the coordinated strategic occupation of the forest canopy, powered not by strength, but by mental modeling. And it worked. By the end of this window, around 20 million years ago, monkeys were not just a niche experiment. They were one of the dominant arboreal mammals in the Old World. Their success set the stage for what would come next. But that part of the story is for another day. For now, it's enough to pause and admit: the branches we so often take for granted as leafy background were, for these small strategists, an entire civilization. A world of gossip, danger, alliances, betrayal, and, eventually, memory. And that brings us back to the question: what happens when brains meet branches? The answer is that trees stop being just plants. They become arenas, battlegrounds, classrooms. And for some ancient monkeys, they became a kind of home. Not because they were born for it, but because they learned how. Which, if you think about it, might be the most monkey thing of all. So the next time you walk under a forest canopy, remember, long before there were humans pointing at fossils and making YouTube documentaries, there were monkeys pointing at each other, and some of them never stopped. And what does it take to turn a dog into a dolphin? That's not a riddle. It's one of the weirdest, most beautifully documented stories in evolutionary history. And the ocean never forgot it. Somewhere around 20 million years ago, in a world still reshaping itself from the chaos that followed the dinosaurs, the land lost one of its strangest animals. It didn't go extinct, it just went home. This was the period when the descendants of four-legged, hoofed creatures gave up the solid ground under their feet and fully committed to life in the sea. These were the early whales. And unlike dinosaurs, they left a fossil trail so absurdly specific that we can almost storyboard their transformation, limb by limb, toe by toe, lung by lung. But let's back up, because to understand why whales look like they do today, smooth, streamlined, echolocating titans, we need to accept something slightly unsettling. Evolution doesn't think ahead. It only messes with what's already lying around. And what it had lying around in this case was a kind of dog. Well, more like a deer with an identity crisis. The ancestors of whales are believed to have branched off from artiodactyls, the even-toed ungulates that also gave rise to cows, pigs, and hippos. In fact, molecular studies suggest that modern whales and hippos share a common ancestor that lived about 50 million years ago. But while hippos stayed semi-aquatic, lounging in swamps and rivers, the other branch started swimming out farther, not for fun, for food. The fossil record tells us that early cetaceans didn't leap gracefully into the ocean, they crept. One of the oldest and most famous transitional forms is Pakicetus, a four-legged, wolf-sized mammal that lived in the shallows of what is now Pakistan. It still had proper legs, still walked, still breathed air through nostrils placed right at the tip of its snout. but it was already showing signs of aquatic ambition. Denser bones, thicker ear structures tuned to underwater sound, teeth meant for snapping at fish. Over the next several million years, these proto-whales drifted through a series of radical body changes. Ambulocetus, literally walking whale, looked like a crocodile that had watched too many dog videos. It had muscular legs, strong enough to push it across land, but also a long, flexible spine for swimming. And it probably moved with the awkward, lurching gait of a seal on land, but was much more agile in the water. Then came Remingtonocetus, a slimmer, sleeker animal with shorter limbs and a longer tail. And eventually, by the time we hit the 15 to 20 million year mark, we find fossils of Basilosaurus, a creature that, despite its name, was not a reptile, but a true whale. Up to 18 meters long, with a sinuous body built for deep dives and fast motion. Its tiny, useless hind limbs still dangled, vestigial reminders of a land-based ancestry. They served no locomotor purpose. Possibly they were used in mating. Possibly they were just evolutionary leftovers. Either way, the ocean didn't mind. But going aquatic is not just about growing flippers and losing your legs. It's a total lifestyle change. The shift required a complete re-engineering of lungs, ears, kidneys, skin, thermoregulation, and, crucially, communication. Modern whales are master listeners. Their entire skull is built to detect and amplify underwater sound. Around this time, the inner ear began adapting to the physics of aquatic acoustics. Sound travels faster and farther in water, but it behaves differently than in air. The middle ear needed to decouple from the skull. Fatty tissues in the jaw and skull began to act as conductors. Eventually, these adaptations would give rise to echolocation in some lineages. But here, in this period, we're watching the scaffolding emerge. Silent, soft steps towards sonar. Meanwhile, the blowhole, that signature nostril on the top of a whale's head, began its upward migration. In early whales, nostrils were still at the front of the snout, but over millions of years they crept back and up, eventually reaching the crown of the skull. This tiny detail is a masterpiece of natural engineering. It lets whales breathe without lifting their heads, a simple tweak that allowed them to spend more time underwater, glide more efficiently, and evolve deeper dives. Their tails changed too. Unlike fish, which move side to side, whales began using vertical tail flukes. The development of powerful tail muscles and symmetrical flukes allowed for thrust-driven swimming that conserved energy over vast distances. Combined with streamlining and insulation from thick blubber, whales had all the tools to leave the shorelines behind for good. But even as they evolved away from land, they never fully let go of it. Modern whales still have vestiges of hip bones. Their embryos briefly form hind limbs before reabsorbing them. Some toothed whales still retain a few hairs around their snouts, and their need to breathe air never went away. Every whale on Earth is still, fundamentally, a land mammal, one that never developed gills. They are forever caught between two worlds, surfacing for breath even as they belong to the deep. By around 20 million years ago, they had reached global waters. The fossil record shows early Odontocetes, toothed whales, and Mysticetes, baleen whales, diversifying rapidly. Odontocetes took the path of precision, sonar, echolocation, prey targeting. Mysticetes took the path of abundance, massive filter feeders capable of swallowing entire clouds of krill. Different strategies, same goal: eat, survive, explore. And they did explore. These creatures weren't hugging coasts anymore. They were moving across oceans, following currents, tracking prey, diving deeper than any other mammal had dared. And their presence began reshaping marine food chains. Whales are not just swimmers, they are nutrient pumps. Their movement stirs the ocean. Their feces fertilize plankton blooms. Their migrations create corridors of life across otherwise empty seas. And when they die, their carcasses fall to the seafloor, feeding entire ecosystems for decades. Even in death, they feed the ocean. It's hard not to admire the sheer absurdity of this journey. A hoofed mammal becomes a swimmer, then a diver, then a voyager of the abyss. It develops sonar, tail propulsion, subcutaneous insulation, complex social communication. All because, millions of years ago, the land was getting crowded, and the water looked like an opportunity. But here's what keeps scientists humble. We didn't know this story fully until quite recently. For most of history, whales were just sea monsters. They were myths, monsters, oil sources, and songs. It took the slow, patient work of paleontologists, geologists, and molecular biologists to piece together their history, bone by bone, gene by gene. And we still don't have the full picture. There are gaps, there are fossil deserts, there are strange anomalies we can't quite explain. But the overall arc is clear. The ocean remembers. And in its memory is the long, strange tale of mammals who went back to the sea and became something entirely new. So the next time you see a whale surface, remember, that's not just an animal. It's a monument to change. It's a breathing echo of a time when feet became fins, when nostrils crawled up skulls, and when the Earth's largest creatures chose silence, pressure, and darkness over gravity and air. And if that doesn't make you feel small and amazed, try holding your breath for 20 minutes. They do it every day. Now the haunting question. If whales did it once, could mammals ever return to land again? If they had to? Because evolution doesn't erase the past. It just builds on top of it, and sometimes in the right bones the ocean leaves the blueprints. This evolutionary exploration wasn't happening in isolation. The same forests that cradled these early apes were also home to evolving birds, insects, and flowering plants. Co-evolution played a role. Fruit-bearing plants may have influenced primate color vision. Changes in canopy structure could have shifted predator-prey dynamics. Even forest fragmentation, driven by slow tectonic changes or shifting rainfall patterns, likely created isolated pockets where different ape populations were subjected to different evolutionary pressures. What survives from this time is less a family tree and more a messy sketch of who might have been trying what, and where, and for how long. And yet, despite the gaps and uncertainties, one theme cuts through the fossil haze. Bipedalism didn't start on the ground. Many of the traits we associate with upright walking, vertical climbing, flexible hips, strong grasping feet, were already taking shape in the trees. Upright posture may have evolved as a way to navigate vertical trunks or reach for food rather than as a first step toward walking savannas. This flips the traditional story of human evolution. Instead of apes climbing down from the trees and discovering upright walking, it may have been the other way around. They were already partially upright, and later some of them took that posture to the forest floor. The irony is that most of these early apes didn't make it. For all their clever adaptations, their flexible joints, and their newfound postures, the majority of Miocene ape species went extinct. Climate change, forest shrinkage, and competition with more specialized species likely thinned the ranks. But a few lineages persisted. Somewhere in Africa, probably during the later part of this period, the ancestors of modern great apes, gorillas, chimpanzees, and eventually humans, branched off from this chaotic arboreal experiment. And they did so not as kings of the jungle, but as survivors of a long and confusing chapter most of us have forgotten even happened. So what does it take to become an ape? Apparently, not much, except a willingness to give up your tail, rethink your entire body plan, climb trees in weird new ways, and then survive long enough for your cousin's descendants to tell your story millions of years later through a screen. What's strange is not that apes emerged, it's that they kept going. Because as with most evolutionary shifts, success is rarely about perfection. It's about luck, opportunity, and the ability to hang on, sometimes quite literally. And that leaves us with a question. If so many different climbing styles emerged, why did only one or two survive? Did evolution favor one path by chance? Or was there something inherently better about the way our ancestors moved through the trees? As we move forward in the story, the forests begin to change again, and the ground starts calling louder. But for now, in this strange chapter of mid-Miocene history, the trees were filled with creatures that looked nothing like us, and yet carried the seeds of everything we would one day become. If you were to travel back to the lush, tangled forests of Africa or Europe sometime between 15 and 10 million years ago, and you were hoping to spot the first ape, you would likely walk right past it. Or maybe more accurately, it would be 30 feet above your head, staring at you in silence, trying to figure out what your deal was. Because the earliest apes were not the barrel-chested tree swingers of modern jungle documentaries, nor the upright proto-hominins we like to call cousins. They were a confusing patchwork of limbs, teeth, and climbing styles. Some of them looked like small, tailless monkeys. Some looked like sloths with a drinking problem. Most of them would be considered evolutionary experiments that never caught on. And all of them were navigating a new kind of world, one where the forest canopy had become a vertical labyrinth, and evolution seemed more interested in trial and error than grand design. This is the Middle Miocene, a time not known for anything dramatic at first glance, and yet underneath its quiet leaf litter, something was stirring. Roughly 15 million years ago, the planet was warm. Not post-dinosaur firestorm warm, but still far hotter than today. Polar ice caps had shrunk dramatically, sea levels were high, and tropical forests blanketed large portions of the globe, including regions that today are dry, seasonal, or stripped bare. These forests weren't just pretty. They were structurally complex, with layered vegetation, dense canopy cover, and a three-dimensional buffet of fruits, leaves, and insects. For mammals, especially those venturing into trees, this offered both opportunity and danger. It's easy to get food in the treetops, but you need a body that won't get you killed before dessert. The key innovation that defines apes and separates them from their monkey ancestors is not intelligence, tool use, or even social bonds. It's how they move. Monkeys generally evolved with long tails and flexible spines built for running along branches. Apes, on the other hand, dropped the tail and started experimenting with suspensory locomotion, hanging, swinging, climbing with their arms instead of their legs. This was not a cosmetic change. It required an overhaul of the entire body plan. Shoulder blades rotated onto the back, arms lengthened, thumbs became more opposable, the lower spine stiffened. All of this allowed the early apes to move through the forest canopy in ways monkeys could not, slowly, deliberately, often upside down. And it opened up new feeding zones that had been off-limits to traditional branch runners. But here's the catch. There wasn't one way to be an early ape. Between 15 and 10 million years ago, paleontologists have identified dozens of now extinct genera that fall into this murky, unresolved category of stem apes. There's Morotopithecus, possibly one of the earliest to show evidence of upright posture, found in Uganda and dated to around 20 million years ago. There's Proconsul, which still had a monkey-like back but may have begun losing its tail. And then there's Dryopithecus, showing up closer to 12 million years ago in Europe, a creature that may have had more advanced climbing adaptations and a diet rich in soft fruits, possibly even showing brain enlargement beyond what you'd expect for its size. None of these were direct ancestors of humans, or at least, not in any clean, linear sense. Instead, they represent a sprawling bush of experimentation, with multiple lineages trying different climbing strategies, limb proportions, and jaw shapes, most of which ended in evolutionary dead ends. The thing is, we're still very much guessing here. The fossil record of Miocene apes is notoriously patchy. Forest environments aren't great for preserving bones, and many early apes died in places where decay beat geology. What we do have are fragments, pieces of jaw, some teeth, partial limbs, that suggest a wide variety of diets and climbing styles. Some species likely moved slowly and cautiously, using all four limbs like modern orangutans. Others may have been more acrobatic, some were solitary, some probably lived in small social groups. The variations tell us that arboreal life didn't demand a single blueprint. It allowed, or perhaps required, diversity, an ongoing test of what worked best in a world made of branches. The fossils begin to thin out. In places where Dryopithecus had been common, we start to find only fragments. In Hungary, a few last survivors hang on for a while. In Greece, Oranopithecus makes one of the final stands. But after 7 million years ago, the fossil record of European apes essentially flatlines. They don't seem to migrate east into Asia in large numbers. They don't leave behind transitional species. They don't get smaller or shift to new diets. They vanish. And for the most part, we don't know exactly why. The disappearance of Europe's apes is still a puzzle made of missing pieces. There are theories, of course. One possibility is that these apes were too specialized for forest life. Their large body size and slow reproductive rate made them vulnerable to rapid environmental changes. Another idea is that competition with emerging monkey species, which were more adaptable and possibly more efficient at foraging in fragmented environments, gradually pushed them out. There may have even been diseases that swept through isolated populations with devastating effect. But the truth is, the evidence is thin. We can see the outlines of the collapse, but not the final blow. Even more frustratingly, we don't have many complete skeletons. Most of what we know about these lost apes comes from jaws, teeth, and partial limb bones. That limits how much we can say about their behavior or ecology. It also makes it difficult to place them cleanly on the evolutionary tree. Some may have been close relatives of the ancestors of gorillas or humans. Others were likely side branches with no modern descendants. All of them are gone. And yet, there's something quietly tragic about their absence. For millions of years, Europe was a second cradle of ape evolution, not just a side stage, but a major arena of experimentation. If things had gone differently, if the climate had stayed wet just a little longer, it's entirely possible that Europe, not Africa, could have been the place where upright apes first walked on two legs. Or maybe it already was, and the fossils were simply lost to time. One particularly enigmatic site is the fossil bed of 𝐓𝐻𝐾𝐌𝐏𝐻𝐒 in Greece. Dating to around 8 million years ago, it offers a snapshot of this vanishing world. Among the bones of giraffes, hyenas, and elephants, paleontologists have found the remains of apes with unusually robust jaws and human-like dental proportions. But whether these represent ancestors, cousins, or evolutionary one-offs is still debated. The bones are too incomplete. The story ends too abruptly. So we're left with echoes. A few molars in a dusty museum drawer, a partial jaw buried under a highway expansion, names in textbooks that shift with each new discovery. Europe's apes were real. They climbed real trees, ate real fruit, groomed each other under real leaves. And then the forests went quiet. Not with a bang, but with a slow thinning of canopy until only grass remained. If there's a lesson in this, it may be that evolution doesn't always reward intelligence or strength or even adaptability. Sometimes it just rewards being in the right place at the right time. Europe's apes had millions of years to try, but when the rules changed, they disappeared. Not because they failed, but because the world they were built for failed around them. Which leaves us with one final uncomfortable thought. How many evolutionary experiments are we walking past today, never realizing they were once contenders? The forest remembers more than we do, and it forgets faster than we can dig. What happened to the other apes that weren't us? That's not just a haunting question, it's a real mystery. Because for millions of years, Europe was not the barren, temperate continent we imagine today. It was a lush, forested world, dense with fruiting trees, climbing vines, and an entire community of primates that once called it home. In fact, for most of the Miocene, the story of apes was as much a European tale as it was an African one. But then, sometime between 10 and 7 million years ago, the forests began to vanish. And with them, almost every trace of Europe's original apes disappeared. Not migrated, not evolved into something else, just gone. To understand this extinction, you first have to picture Miocene Europe not as a modern continent but as a subtropical mosaic. Around 10 million years ago, much of southern Europe was still covered in dense woodland, interspersed with lakes, wetlands, and patchy open areas. This was a time when apes like Dryopithecus and Oranopithecus thrived. These were not modern apes, but they shared many of the traits that would one day define our lineage: advanced locomotion, flexible joints, strong grasping limbs, and possibly even rudimentary social behaviors. Fossils from France, Spain, Hungary, and Greece show us a continent teeming with primate life. They weren't all ancestors of humans, but they were all part of the same arboreal experiment. Large-bodied apes adapting to a world that was still mostly vertical. But things were already starting to fray. Climate shifts in the late Miocene brought a slow but relentless drying trend. Temperatures cooled, seasonality increased, and most critically, rainfall patterns began to change. This wasn't an overnight collapse. It was more like a long goodbye. Forests didn't vanish all at once. They thinned, retreated, and fragmented into isolated pockets. And that's a death sentence for species that depend on continuous canopy to find food, mates, and shelter. Once the forests became patchy, populations became trapped, isolated, and vulnerable. Genetic diversity plummeted. Food became scarcer. The risk of extinction multiplied. This wasn't just bad news for apes. It was part of a broader ecological turnover. As the forests died back, they were gradually replaced by more open woodland, scrubland, and eventually grass-dominated habitats. These new environments favored different animals, especially hoofed mammals like antelope and horses, which could run, graze, and tolerate drier conditions. Insects shifted, birds shifted, carnivores shifted, and the apes? They didn't shift fast enough. Imagine a forest slowly forgetting how to be a forest. Not all at once, not with a single moment of catastrophe, but gradually, over millions of years, as the rain began to hesitate, the clouds became less generous, and the green gave way to gold. Between 7 and 5 million years ago, East Africa began to dry out. And though no one was around to see it happen, the land was taking its first steps toward becoming something else entirely. The age of the jungle was breaking down, not with an asteroid, not with a bang, but with a long, aching sigh of climate shift. It began with the rain, or rather, the lack of it. The once lush Miocene forests that had stretched across Africa, thick with canopy and echoing with life, started to thin. We can trace this transition through subtle clues embedded in the landscape itself. Soil carbon isotopes reveal the creeping dominance of C4 grasses, those hardy, sun-loving plants that thrive in open, arid spaces. The pollen record shifts too, showing a drop in forest-loving flora and a corresponding rise in grassland vegetation. It is not a clean transition. It is messy, uneven, and full of microclimates. But the trend is undeniable. The forest was retreating, and the savanna was taking its place. Behind this transition were powerful climatic gears grinding against each other. The movement of Earth's tectonic plates had long been nudging East Africa upward, slowly elevating the landscape and changing its rainfall patterns. Higher elevations meant more runoff, less moisture retention, and cooler temperatures. Combined with shifting ocean currents and the long-term wobble of Earth's orbit, these changes helped dry out vast regions that had once been green. The Indian Ocean monsoon weakened, the once reliable wet seasons fractured, and over tens of thousands of years the rainforest didn't just disappear, it morphed into something else. What replaced it wasn't a barren wasteland. It was a new biome with its own rules and players, the savanna. Unlike forests, which layer their life vertically, from undergrowth to mid-canopy to towering emergence, the savanna spread its drama out horizontally. Here, life was exposed. Light raked across the land without mercy. Temperatures swung wildly between scorching days and cold nights. Water came unpredictably. It was a world that rewarded mobility, awareness, and adaptability. In short, it was not a place for those who had evolved to sit still. This transition didn't just reshape plants. It began to rewrite the entire fabric of animal life. Fossil sites across East Africa show a marked increase in grazing species, those that fed on the tough grasses now dominating the landscape. Hooved mammals began diversifying. We see early relatives of antelope, pigs, and horses shifting their diets, changing their teeth, and covering more ground. Predators adapted too, with fossils showing a shift toward cursorial hunting, chasing prey across open spaces instead of ambushing them in dense foliage. But the most intriguing question is not what happened to the grazers, it's what happened to the climbers. The species that had once relied on branches, shadows, and vertical refuge were now facing an existential problem. With the forest vanishing, so too were the shelters it provided. And that raised a problem that would eventually redefine an entire lineage. How do you survive in a world where the ground is no longer optional? We don't yet know when the first primates stepped onto the savanna floor and didn't go back. But we can see the conditions beginning to form here, in this time period between 7 and 5 million years ago. The forest didn't vanish overnight, and it didn't vanish everywhere. But its patchiness meant that arboreal species were forced to move between tree islands across open land. That may not sound dramatic, but it was a fundamental shift. Movement became riskier, predation pressure increased, and new strategies had to emerge, strategies involving vigilance, travel, and cooperation. One fascinating clue comes from the changes in tooth enamel among primates from this era. Thicker enamel suggests a shift away from soft forest fruits to tougher, drier, ground-based foods. We also begin to see skeletal hints, longer legs relative to arms, changes in pelvis structure that imply a more ground-oriented lifestyle. These are not yet the fully upright hominins that will walk later. These are transitional creatures, caught between trees and turf. Geologists and paleoclimatologists have pieced together this story through core samples, dust layers, and stable isotope analysis. Dust blown from East Africa into the Atlantic has increased in these epochs, confirming the expansion of arid zones. Ancient lake beds show fluctuations in water levels that match periods of aridity. Even marine records from off the coast of West Africa show terrestrial fingerprints, as wind patterns carried the continent's drying heartbeat out to sea. It's tempting to think of savannas as permanent fixtures of the Earth's ecology, but they are transient, dynamic systems. Between 7 and 5 million years ago, they were still young and forming, and they didn't arrive gently. They came as an upheaval, a transformation that tested the resilience of every organism that had adapted to a wetter, darker world. This era gave rise to a landscape of uncertainty. It was a place that didn't offer the dependable abundance of the forest nor the stability of the full grassland systems to come. It was an in-between space, a biome in flux. And in this instability, some lineages floundered, others adapted. A few began a journey across the ground that would eventually take them into an entirely different future. And here is the haunting question. Was this environmental pressure enough by itself to begin nudging certain primates toward new ways of moving, thinking, and surviving? We don't know for certain. But the stage was set, the trees were breaking up, the ground was opening wide, and something, somewhere, was watching from a branch, eyeing the space below, calculating the risk. The forest was still there, but just barely. And for the first time in tens of millions of years, the Earth was whispering a different kind of invitation. Come down, try walking. Let us begin this last part of the story not with certainty, but with a shrug, the kind only a humble primate with a pickaxe and a few jawbones can offer. Somewhere between 5 million and 3 million years ago, in the sedimentary basins and rift valleys of East and South Africa, something began to shift. The forests were no longer safe havens, and the trees no longer enough. A clever ape, or maybe just a desperate one, began to experiment with a new posture, upright, tentative, unfinished. This was not a final form, not yet the full striding gait of the genus Homo, not yet the ambitious sculptor of fire or stone, but still a movement towards something new. In the highlands of Ethiopia and the low scrublands of Chad, we've found traces of this tentative step, fossilized bones that suggest a changing relationship with gravity. The pelvises of Sahelanthropus chadensis and Auroran tuganensis, discovered in sediments dated to between 7 and 6 million years ago, hint at an upright stance, but only barely. Their skulls tilt atop the spine in a way that suggests balance while standing. Their femurs bear the tensile stress markers of a species that walked sometimes on 2 feet, and sometimes not. By the time we get to Ardipithecus ramidus, around 4.5 million years ago, the evidence grows stronger. A divergent big toe, useful for climbing, remained. But the pelvic blades, shortened and widened, suggest weight-bearing consistent with bipedality. In plain terms, we are looking at a creature not quite adapted to walk, but no longer only built to climb. The question scientists return to again and again is, why? Why did our ancestors, or cousins, or maybe just evolutionary experiments, begin to stand upright in the first place? Was it the open landscape, the need to reach food in low shrubs, carry objects, or simply keep cool in the savanna sun? All of these are plausible. None are definitive. Upright posture may have been less about walking than balancing, an adaptation to a mixed terrain where moving between trees and across clearings required flexibility more than efficiency. Whatever the cause, the outcome was irreversible. Once the architecture of bipedality began, it set off a cascade of anatomical shifts that would redefine what a primate could be. The spine bent into an S-curve. The foramen magnum, the hole where the skull connects to the spine, migrated underneath the skull, balancing the head atop the body rather than behind it. The pelvis compacted, reshaped into a bowl that could support upright organs and a shifting center of gravity. Knees developed locking mechanisms, ankles changed, and feet lost their grasping curl. These transitions did not happen overnight or even in a single lineage. They represent mosaic evolution, a process by which traits change at different rates across different populations over millions of years. This is the murkiest part of the fossil record. The bones are few, the dates debated, and the evolutionary relationships still unresolved. What we know is built from slivers, a molar here, a toe bone there, and a frustratingly large number of extinct branches. Some may have led to Australopithecus, the genus that includes the famous Lucy. Others were evolutionary dead ends. The story is not linear, it is braided, full of starts and stops, and shaped by local environments we can only partially reconstruct. We also cannot separate bipedality from its side effects. Walking upright changes what you can carry. It frees the hands. It narrows the birth canal. It shifts the rhythm of life itself. Slower maturation, longer childhoods, more complex social structures. And yet none of these were necessarily the reason for the change. They were consequences. Evolution does not build with blueprints. It tinkers, sometimes blindly. So here we are, on the edge of 3 million years ago, with a creature who is not quite us, but no longer what came before. They are walking more than climbing. Their world is drying, cooling, and demanding new strategies. They are not Homo. They are not yet telling stories. But they have made a choice, or perhaps had it made for them, to live on the ground, on 2 feet, under a sky that now contained more open sun than sheltering canopy. And that one evolutionary gamble would set the stage for everything that follows: fire, tools, migrations, empires, dreams. But none of that has happened yet. Not here. Not now. All we know, all we can barely see in the rock, is that someone took the first step. And somehow, it mattered. What would have happened if they hadn't? If bipedality had failed, or reverted, or splintered in a different direction? Would the Earth still have storytellers? Or would it still be a planet of forests and 4-legged apes, climbing forever? That is where we leave them, upright, uncertain, and just beginning to walk. And that's where we leave them, not yet human, not even close, but standing, not with confidence, but with potential. Somewhere between 5 million and 3 million years ago, a clever ape tried something strange and unfinished. They stood up. They walked. Not far, not fast, but enough. Enough to change the rhythm of bones and birth, of movement and memory. And that quiet decision, or accident, is what made everything after possible. Not guaranteed, just possible. From there would come the long arc of fire and language and cities and stories. But in this episode, we stayed with the early ones, the ones who came after the asteroid but before the myths. We wandered with the creatures who inherited a broken earth and made it sing again, with fur and teeth and forests. We saw whales walk and apes fall. We watched grass rewrite the rules. We followed mammals from the shadows of extinction to the strange, upright gamble that might eventually lead to you. So thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life. And tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.